Rajguru, it's time now in about 15 seconds or so. Should we start, or do you think we still need to wait for a minute?
You can start in time. Maybe give 1 minute probably.
Okay. So
signing in, maybe just 1 minute.
Okay. Okay, we start then.
Yeah, go ahead.
Okay. So welcome all to the third session of the final day of this conference. In this session, we have 2 invited talks and a contributor talk, and the topics will cover solar activity and irradiance. For the invited talks, I will give a note at 20 minutes mark so that you have 5 more minutes to finish your talk and then 5 minutes to discussion. And for the contributor talk, I give a note at around 12-minute mark. So the first presentation will be an invited talk by Professor Ilya Usoskin on long-term activity of the sun. So Professor Usoskin, I invite you to share your screen and then start the presentation. Thank you.
Hey, good afternoon in India, morning in Europe. Do you see my screen?
Yes, we do see, yes.
Okay. So I would like to thank the organizers for inviting me to this meeting, and I will very briefly tell about long-term variations of solar activity. As long-term, I mean solar cycle and beyond that, and the current state of the art in this field. For many reasons, we want to know variability of solar magnetic activity, and our direct measurements of them can extend for a few tens of years of when we can make good observations and mapping magnetic features on the sun, optical measurements which can be converted into magnetic features extend for about 100 years. Please observe the logarithmic time scale in this plot. Geomagnetic measurements, which also can represent in a way solar activity via geomagnetic proxy, also extend backward for around 100 years or more. Then there are, of course, sunspot counts and drawings which extend for 400 years now, but the quality is not uniform. While we are pretty much sure about the sunspot variability over the last 100 years or so, it becomes much less accurate when we go beyond 200 years ago. And there was a big discussion, you probably know, recently about the revision and updates of the sunspot series, which is still ongoing. So it's quite uncertain toward the early age of the data. Then, of course, there are historical records of aurora sightings in different historical documents and chronicles. But this data can hardly be converted into a quantitative index of solar activity with homogeneous quantity. So it's only some qualitative indication. And same can be applied for naked eye sunspot observations, which were made not in a scientific manner, and it's hardly possible also to convert it into a uniform quantitative index of solar activity in the past. So it looks from this data that we would have few hundred of years of more or less reliable data, and then nothing more beyond that. But luckily for us, the Mother Nature makes a very good job and provide us so-called proxy data of cosmogenic isotopes, where the nature makes half of work for us. So it stores the information about solar activity in the past in natural archives, and our task now is only reveal this information. The cosmogenic isotopes, of which I will say in a few minutes, provides a homogeneous of stable quality data set for around 10,000 years for the Holocene, for the period of warm and stable climate on Earth, and potentially can go even beyond that, but not at the present time because of very uncertain climate effect on cosmogenic isotopes. So as you know, of course, the solar activity in particular as reflected in sunspot numbers is dominated by 11-year cycle, but also depict a big deal of longer-term variability, which expressed in different amplitude of the sunspot cycle, or even complete disappearance of sunspot cycle during the so-called Maunder minimum period in the second half of the 17th century. So despite the 11-year cycle, there is a strong variability of solar activity on longer time scales. And the only way to study that beyond the few hundred years is the cosmogenic proxy data. And first, let me say a few words about cosmic rays at Earth. Cosmic rays are highly energetic nuclei coming to Earth from our galaxy and beyond. And at the first approximation, the flux of cosmic rays can be considered as constant beyond the heliosphere, the solar system. And then the sun, through solar wind and interplanetary magnetic field, which are defined by solar magnetic activity, modulate the flux of cosmic rays inside the heliosphere. So the flux of cosmic ray arrives to Earth already modulated by the solar activity. And then near Earth, we have an additional shielding related to the geomagnetic field. So altogether, on any specific location on Earth, the flux of cosmic rays is double modulated by the solar magnetic activity and geomagnetic field. And this just to show the variability of cosmic ray flux near Earth during solar minimum condition, solar maximum condition, and the local interstellar spectrum, which means there is no solar modulation at all. And you can see that in the low energy range of a few gigaelectron volts, the variability is by an order of magnitude, which fades quickly with the energy of cosmic rays. And this can be observed if we just have a simple look at the sunspot number counts for the last 70 years and compare with the intensity of cosmic ray flux also recorded at Earth. They're very highly anti-correlated, reflecting the solar modulation of cosmic rays. So at first look, it seems very simple. But later I will go into more details. What happened next with when a highly energetic cosmic ray particle, and mostly protons, but it can be also heavier species, enters the Earth atmosphere, which is very thick. We have around about 1 kilogram of air per 1 square centimeter of the Earth's surface, which is a thick around 10 meters of water equivalent, which means that the cosmic ray particle, say proton, will interact with one of nuclei of atmospheric gases. It can be oxygen, nitrogen, or whatever. Since energy of the incident proton is very high, the products of this first nuclear collision can be also sufficiently energetic, producing secondary, tertiary, and so on collision before the products of this, it's called cascade or shower, reach the ground. On average, there are about 10 collisions for between the incident particle entering the atmosphere and the cascade reaching the ground. And in each of these collisions, nuclear collisions, different products can be produced, and it leads in particular to formation of quite rare radioactive isotopes. Of special interest are the radiocarbon, carbon-14, which is a result of a neutron capture by nitrogen nucleus, and also spallation reactions leading to formation of beryllium-7, beryllium-10, chlorine-36, and so on isotopes. An important thing is that these isotopes are radioactive, which means they decay after few days or millions of years, but they decay, so they cannot survive on Earth since the formation of solar system, and they are not produced in the natural cycle of Earth. So they only can be produced by cosmic rays before the nuclear explosions made by human beings. Therefore, they called cosmogenics. And if you know the amount of cosmogenic isotopes produced some time ago by cosmic rays, we may estimate solar activity in the past during the time, and it can be done with a lot of simulations and modeling. But overall, for the given production rate of cosmogenic isotopes some moment back in time, and the knowing of the geomagnetic field at that time, because it provides additional modulation, we can estimate the level of solar modulation of galactic cosmic rays from this kind of plot. And the accuracy of this method is very high. It's of the order of a few percent. The largest source of accuracy for these long-term reconstructions, so activity is related to geomagnetic field, so-called paleomagnetic or archaeomagnetic models. And this plot shows several paleo reconstructions, and you can see the uncertainty between different reconstruction is quite high. Although they agree on the very long-term pattern, they may disagree on shorter time scale. So this is the largest uncertainty so far of the solar activity reconstruction for the period of the Holocene. So what happens with the cosmogenic isotopes after they are produced in the atmosphere? Here we may consider two most important isotopes. One is the radiocarbon or carbon-14, which is after production, it gets quickly oxidized to carbon dioxide, like just a normal carbon dioxide, and then takes part in the normal carbon cycle, which includes oceans and atmosphere, biosphere. So it's a very long cycle. It takes, because it's chemically, it takes chemical reactions. It is included in carbon cycle. Therefore, it can be considered as a first approximation globally mixed in the terrestrial system. And where it is measured in biosphere, or actually in 3 rings, because trees just absorb carbon from air to build its body. And the rings are annual, so just counting the rings, we can exactly know the period in the past to which this ring corresponds, and this gives the radiocarbon for the exact year in the past. Another important isotope is beryllium-10, which does not have any chemical reaction. It's a metal, and it's normally stick to aerosols and falls out with aerosols and just then stay where it's deposited, and it's measured in typically in polar ice, which is also stratified. By an important thing here is that there is no cycle of radiocarbon. Once it's deposited, it never recycles back. So after the production, which is modulated by inside the heliosphere, and additional geomagnetic shielding, which affects both isotopes in the same way, there is local climate, regional or even global climate, which affects the transport and deposition of the isotopes in the Earth atmosphere, and it affects very differently the two isotopes. As I said, radiocarbon is involved in the global carbon cycle. Beryllium-10 is mostly deposited regionally, which means that the two sources of heliospheric or solar modulation and geomagnetic shielding is the same for the two isotopes, but the deposition is different. And that's very good, because then we can try to disentangle the production effect and the depositional effects. And just to show that it's not very easy to neglect the depositional effect, this shows the annual mean deposition of beryllium-10 as a location on Earth. And you can see the difference may be more than an order of magnitude between the high deposition and low deposition rates. And many ice cores are located in Greenland, and you can see there is a very strong gradient between Greenland and the Atlantic region, and just shifting this depositional pattern slightly may affect the measured concentration of beryllium-10 in Greenland. This makes it hardly possible to use cosmogenic isotopes before the Holocene, during the Ice Age or transition from the Ice Age, where this pattern may be changed and we don't know exactly how. But anyway, for the Holocene, it's quite stable, and then we can come to the results of the reconstruction of long-term solar activity based from cosmogenic isotopes. And here first I show reconstruction of the decadally resolved solar activity based on radiocarbon and beryllium-10 data for the last 3 millennia. Why 3 millennia? It's because the geomagnetic field is relatively well known for that period. It's based on archaeomagnetic data when humans use clay to produce some kitchen stuff. The clay keeps the magnetic record of magnetic intensity, and then using data from different archaeological sites, the geomagnetic field can be reconstructed with quite high precision. When going before the development of the human civilization, we need to rely on other ways of archiving, like sediments or volcanic lava, and this is less precise because it's not so widely distributed. Anyway, the last 3 millennia are quite good in the sense of knowing the geomagnetic field, and this is the reconstruction of solar activity. And what we can, it's compared with the known sunspot record, and as you can see, there are several typical features. One, there is overall variability, of course, and this is, we can safely consider this is solar activity variability. There are some periods of sudden drop of activity for around 100 years or less, of several decades. And one of them coincides exactly with the Maunder minimum of solar activity, which indicates that these drops are also grand minima of solar activity, similar to the Maunder. Then the activity most of the time stays of roughly the same level, which is the mean level of solar activity. And there was one very active period in the second half of the 20th century related to the modern grand maximum of solar activity. And if we plot the probability density function of the values of solar decadal, so sunspot cycle, solar cycle is not observed here; it's decadal resolved data. We can see that there is a general mode of or regular mode of activity, then statistically highly separate grand minimum mode. So there is a bump. And for the grand maximum, statistics is too low. We cannot say whether it's a special mode or statistically different mode or just a non-Gaussian tail of the distribution. Now I show the reconstruction of activity of the whole Holocene, which is around 12,000 years back. Also, you can see different the variability on different scale. The most of the time, it's a moderate level between the blue and the red lines. There are many drops or these grand minima periods, which are indicated by blue here. An interesting thing that they cluster together. They tend to cluster together. For instance, quite recently, there was a strong cluster of grand minima. You see one Maunder, Spörer, Wolf, Oort minimum. Then almost nothing, a couple of other minimum, again, no minima, and again. So they tend to cluster together. And the separation between clusters is roughly 2 millennia. And within the cluster, the separation is quite strong with around 200 years.
5 more minutes.
Okay, thank you. And there are also periods of very high activity similar to the modern grand minimum, for the modern grand maximum, but they are not regular and they tend to appear in the early part of the series, probably related to the climate effect that we don't know. Overall, we may say that around 17% of the time, the sun spends in the grand minimum condition and around 10% in the grand maximum condition. Quite often you may hear about periodicities in the solar activity, and here it's not very clearly defined beyond the 11-year solar cycle. There is, of course, the famous Gleisberg or centennial variability, which is not very strict. Periodicity, it's rather a typical time scale of variability of between 60 and 140 years. Then there is very stable Zeus, called Zeus or de Vries cycle with a mean period of 210 years. And as I said, it appears as clustering of grand minima. You see there is power only around grand minima periods. Then sometimes there are mentions of the so-called eddy or millennial cycle, which is not statistically significant through the whole period. Then there is Hallstatt cycle, which is also not statistically significant, but very clearly visible. I will show it in the next slide. And sometimes there is discussion of the 6,000-year period, but with 10,000 years data, it can be hardly defined statistically, and it seems to be more related to climate. Here, just a few illustrations of the periods of the cycles. The Hallstatt cycle, which is shown on the bottom panel, is exactly the same, amazingly, in the radiocarbon data. The the blue curve, and beryllium-10 data. Red curve, it's synchronous and very very stable, which implies that most likely it's the production. So it's either geomagnetic field or solar activity, and we don't know any cycle like this in the geomagnetic field. For the longest 6,000 year cycle, it's only observed in the radiocarbon, but not in beryllium-10 data, which may suggest that this is climate because it affects differently the two isotopes. And here I want to present the very preliminary result, which will, we hope, appear soon, where for the first millennium annual data from radiocarbon entry rings published in Nature Geoscience a month ago, we are able to reconstruct this the 11-year sunspot cycle on the last millennium, but I will not discuss it now, just to emphasize the preliminary data. And then I switch to the summary that cosmic ray variations via cosmogenic isotope is the only source information on quantitative studies of solar heliospheric variability over the Holocene. The sun spends 3/4 of the time in the regular moderate activity mode, about 1/6 in the grand minimum and 1/10 in the grand maximum states. And there are several intermittent cycles in the solar activity found during the last 10,000 years, ranging from Gleisberg, Zeus, Devry, Hallstatt cycles. Other cycles are insignificant and still not confirmed. And also, don't try to predict solar activity using these cyclicities, because it's not strict periodicities, it's only some typical time scale variations. And thank you, my time is over.
Thank you, Ilya, for keeping up with the time. And now the floor is open for questions. If you have any question, please raise your hand and then we will call. Okay, the first question is from Dibyendu Nandi. Please go ahead.
Hey, Ilya, good morning to you. So thank you for reiterating that point about predictions and not trying to make predictions based on fitting past cycles. I think that's an important point for the community who are working on solar cycle predictions. Question that I have for you is based on the PDF that you showed. For the, I'm getting a lot of feedback. Okay, so yes, exactly. Would it be fair to interpret this to imply that the grand maximum phase and the regular phases are qualitatively similar from the perspective of the dynamo that is working during these phases, whereas the nature of the dynamo during grand minima phases is distinct from this other phase?
Yes, thank you for the very good question. I would say exactly the same way. So I agree fully with your interpretation that we cannot distinguish now whether the grand maximum is as a separate mode just from statistical analysis. But grand minimum is definitely statistically different from the regular mode.
Thank you. I think you make a very important point, and I think this agrees with some of the stuff that we have been postulating, but we'll discuss this later. But thanks for this point.
Arnab, would you like to ask your question now?
So Ilya, it's a really fascinating talk. So my question is that you pointed out that during the Holocene, whole period of Holocene, the deposition pattern of beryllium-10 over different regions of the world have remained stable, and that's why you can use it for reconstructing this activity of the Holocene period. And about this pattern being stable during the whole Holocene, is that an assumption or is there any hard evidence for that?
This is an assumption, but it's not a blind assumption. So there are, of course, a lot of numerical modeling made by paleoclimate community, not specifically related to the beryllium-10 deposition, but at least the pattern of the ocean circulation is modeled quite well, and this is the most important thing of the isotope deposition, because especially Gulf Stream for Greenland. Another thing is that in Antarctic, climate is very stable, and about half of ice cores used for beryllium-10 are from Antarctic, and we can compare. If they agree between Greenland and Antarctic, this means everything is under control. If they disagree, then it means a problem. But so far they agree quite well, because patterns are very much different in Greenland and in Antarctica, in Central Antarctica.
Okay, thank you. So is there any realistic hope that within the next few years, we shall know about these patterns more before Holocene and extend the history more?
Yes, we do hope. There are modeling going on, but still the accuracy is not sufficient. But yes, there is a hope. More and more data we get, and the better and better models become, we do hope that we will be able to go beyond the Holocene.
Thank you.
Okay, one last question from Oscar Steiner. Would you like to ask the question directly by unmuting your mic?
Okay, I can do. I just got the impression from one of your diagrams that the grand minima tend to occur shortly after the grand maxima tend to occur shortly after a grand minimum. Not after every grand minimum, but when there is a grand maximum, there has been a grand minimum shortly before.
Well,
significant.
You may study that, and actually there was a couple of studies I can recall, work by Fadil Insiaglu 2015, where they tried to study this kind of relation. They did find something that there is a tendency, but it is not statistically significant. So the statistics is not sufficient to make a very strong constraint out of that.
Sure. Thank you.
So Vidya, do you have a short question?
My question is very short actually. So I like this bimodal distribution of sort of bimodal distribution of sunspot, but I just wondering like how reliable, like you are very confident that this distribution which represent the grand minima phase is statistically very strong. Okay, I know this paper. Okay, I have a paper follow up to your paper. So, but still, I just want to know like how statistically strong this.
Yeah. Yes. The grand minima has statistically very strong separation. So you cannot really explain this bump as at a slightly non-Gaussian tail of the distribution. You need really strong changes. But there are also other patterns, as you can see, for instance, here. Drop and rise are always very fast. It's not considered just in the distribution, but you can consider them. So it's not a kind of a gradual decrease as you may expect if it would purely random. It's always very fast drop and very fast recovery. It again, you cannot see it from the distribution. Distribution is just statistically we estimate that it's significantly different from the tail of the regular distribution. But there is also other pattern which make it quite distinctive in other way.
Okay.
Does it answer the question?
Yeah.
Okay, thank you. If you have any further questions, then please type them in Slack, and then we will continue the discussion there. So Ilya, could you please unshare your screen then?
Yes. Thank you all for the good questions.
So the next talk is from Vibhuti Kumar Jha. Please share your screen and I will give you a 10-minute mark.
Okay, can you see my screen?
Yes. Could you make it full screen?
Yeah.
Yes.
Okay. So first of all, thanks to the organizer to giving me this opportunity to talk about my work. So today I'm going to talk about the signature of quenching. It is actually the continuation of the talk given by Vidya Vinay Karak. So he has already talked about one of the mechanisms that can quench the solar dynamo. So let's start with this is just for the completeness. Everyone, like all of us, all are like familiar with these things. So this is a very basic, this is typical white light image of the sun where we see the few dark spots sometime. And then if I look at the magnetogram image at the same time, we see there are some dark and bright, that is the magnetic field. And we can clearly see these are the bipolar regions, and we call it as a bipolar magnetic region. And now one thing that is important for the bipolar region is that they are tilted with respect to equator, and we call it as a bipolar region has tilt. So now Joyce has discovered that the tilt of the bipolar region depend on the latitude of the bipolar region. So here I have shown that this is a plot taken from the Stenflo and Kosovitsev 2012 paper where they have used the MDI data and shows that shows the Joyce law, that where you can see the tilt angle depend on the latitude of the bipolar region. And this is the mathematical form of the Joyce law, where you can see the gamma equal to gamma naught sine of lambda. Lambda is the latitude. So now let's try to understand what is the physics underneath for these tilt angles. So in 1993, De Silva and Chaudhary has given one idea about that since we know that the bipolar regions are formed when the magnetic flux tube rise from the solar convection zone to the photosphere. During their rise, there will be diverging east-west velocity, and since there is a velocity near the loop apex, it will experience the Coriolis force, and that Coriolis force will cause the tilt in BMR. So later on in 1994, Fan et al. Has given this relation, tilt angle depend on how the tilt angle has related with the strength of magnetic field in the flux tube as well as the flux in the tube. So this is the slide that I have taken from the Vidyada, and this here, now important point is that since I already told this is the continuation of the talk given by Vidya Vinay Karak. So he has mentioned that since all the solar cycles are not same, and we need, particularly in the Babcock latent type dynamo model, we need some non-linearity in the model to somehow suppress the growth of the solar dynamo. So there are some mechanisms like differential rotation, meridional circulation, and turbulent transport, but one of the most important mechanism that play important is in the Babcock latent type dynamo model. So in that particular dynamo model, latitudinal quenching has been already discussed by Vidya Vinay Karak. So right now I'm going to talk about the tilt quenching, how the tilt can affect the solar dynamo. And particularly I will talk about the observational aspect of the tilt quenching. So just to give the brief overview of the tilt quenching. So tilt quenching has been routinely used in this type of Babcock latent type dynamo model. So these authors have used this type of and somewhat ad hoc quenching in the tilt angle, where you can clearly see they have the relation, they have used the strength of magnetic field. Magnetic field will be able to suppress the tilt in the bipolar region. And later on, Karak and Misech, and then Lemmerle and Chervanov in 2017 used this type of quenching in their simulation, and they were able to produce the variation in the solar cycle. So here it will tell about this is the important for the solar dynamo point of view. So I am going to look about is there any evidence for observational evidence that there is an existence of tilt quenching in the bipolar magnetic region. So I have used the data from SOHO and STO Then first task was to identify the magnetic bipolar region. For that, I have used the method similar to the Stanflow and Kosovice, but with little modification for our purpose. Then I have, of course, extracted the different physical parameters for all those bipolar region from the magnetogram taken from SOHO and STO. So this is the one of the example that where you can see they have clearly detected the bipolar region from the magnetograms. So since the Stanflow and Kosovice's math, they have only applied their method on the MDI data. So I have extended their work to the HMI also. I have applied that method to HMI data, and you can clearly see that this method is perfectly working on both of the data set. I have taken the same, like almost same time data from both the instruments so that you can compare it. Now, while detecting the bipolar magnetic regions, I have also calculated the maximum absolute field strength in the bipolar regions. And when I have plotted the distribution of these maximum magnetic field, I found something interesting that this maximum magnetic field has somehow like a bimodal distribution. So then next thing was to just look for the another instrument, that is HMI, and this behavior is also present in the HMI data. So this is nothing to do with the instrument. There must be some physics behind that, or this is really present in the data set. So now task was to try to understand what are these two peaks. So to understand that, there are like ideas about the two type of dynamo in the solar dynamo community, like global dynamo and local dynamo. So it came to our mind, maybe it could be due to there is one class of BMR that is coming from the local dynamo and other coming from the global dynamo. So to understand that, what we have done, we look for the magnetogram as well as continuum images at like almost simultaneous continuum images. And interestingly, we came to know about that. Like if you look at, like here I have shown the red square, like rectangles, where you can see these red rectangles are correspond. If you look at the continuum image, you will see some dark spot. But another class of bipolar region where you will not see any dark spot, similar for HMI data as well. So this could be due to the instrument limitation and our detection method, because the magnetic field strength is not so strong to like suppress the intensity, and we will see the intensity contrast. When we plotted the distribution of these two classes separately, you can clearly see that one class with BMR with spot and BMR without sunspot, not sunspot. You can clearly see one peak correspond to the BMR with no sunspot, and another class is BMR with spot. So now it's gives there are two classes of BMR. To check it, we have also plotted the butterfly diagram. But interestingly, there's no difference in the butterfly diagram. So the origin for all these BMR are same, and they both are coming from the same mechanism. So this was the one result, that even though that there are two classes of BMR, we didn't find they are not coming from the two different type of dynamo. Now there is another thing that is interesting with this plot is that since we have not tracked the BMR for their lifetime, so there's a possibility that this is in the initial phase and this is in the later phase. So if it is the case, then from the sunspot distribution, area distribution, we have seen that the log normal distribution, there should not be the bimodal. So now currently, like we plan for we will track the bipolar regions and look for it's consistent or not. So currently that is another task that I'm currently working on, to track all those bipolar regions for their lifetime, or either like till the disk passes, so that we will be able to see the strength of magnetic field. Now coming towards the main aim of the work, that was the variation of the tilt angle with the strength of magnetic field. So just to remind you that this is the Joyce law, and we have plotted this gamma naught with respect to the maximum magnetic field in the BMR. So what we have done, we have taken the bipolar region which had like a magnetic field in the particular range and bin size of 500 Gauss, and then fitted the Joyce law, and we get the gamma naught. So here I have plotted this gamma naught with respect to the strength of magnetic field. You will clearly see there is an increase in the gamma naught, and then up around 2 kilogauss, it started decreasing. And this behavior is present in both the data sets. Now, while doing that, since there is some scaling factor between the HMI data and MDI data, I have taken care of that. So, and here, if I show you this relation that is given by Fan et al. So I have plotted this dotted line here. So again, this is the flux, and I have used this relation. You can see that in the upper limit here, it is somehow in agreement, but not in the behavior of the curvature of this curve is different. Here in the another plot, I have also plotted the same gamma naught with respect to the maximum, like the flux in the BMR. But since we don't have the much data, so this, even though there is a decreasing trend in MDI, but it is not in HMI data, but it is not conclusive to say anything about the tilt quenching. So now since I have already mentioned that this type of ad hoc quenching is used in the solar dynamo, particularly in a Babcock-Layton type dynamo model. So I have, instead of square, I have used here n, and I have fitted this relation, this data. And what I got is n equal to 5.8 and the maximum magnetic field around 2.9 kilogauss. So, and now this...
Two more minutes, sorry.
Okay. So this gives us the hint about that. This is, since we have only 3 data points, we can't say much about this. We have to either wait for the stronger cycle so that we can get a BMR with even strong magnetic field, or better instrument, because MDI has a limitation of 3 kilogauss. Like if the magnetic field strength is more than 3 kilogauss, you cannot trust on that data value. So this also somehow in agreement with this Dashi et al. Paper in 2010, where they have used the Kodaikanal data, and they have shown that in, from the white light, that the tilt angle has anti-correlation with the strength of the cycle. So this also gives that the strength of the cycle, that means the stronger magnetic field in the cycle, it somehow affecting the tilt, and these two results are in agreement. But now since we have also have the data from last 100 years from the Kodaikanal Solar Observatory, so I have started working on the Kodaikanal white light data. But problem with the white light data is that we don't have the magnetic field information. But it is since we have a data, we can use it somehow. So we have detected the pseudo bipolar region. In white light images, we call it as a pseudo bipolar region because we don't have the polarity information. That assuming the Hill's law is valid for all, that is not correct. And when we have plotted this mean tilt divided by mean latitude with respect to area, we got that after some point, it is start decreasing. And if I see the point where it is a deflection, it is around 400 millionth of hemisphere, that corresponds to 2 kilogauss. And it is also in the agreement with the what I got from the magnetogram data. So this relation is I have used the relation between the maximum magnetic field and area that is derived from the HMI and MDI by Tlatov et al. In 2013. So this is the end of my talk. So summary, I have used the line of sight magnetogram and intensity continuum from MDI as well as HMI data. Our magnetic field distribution was interestingly came out to be the bimodal. And then we have also seen that the tilt decreases with the increase of magnetic field in the BMR. Now this is play a very important role for the understanding of solar dynamo, and it gives the indication of nonlinear quenching that is currently used in the Babcock-Layton type dynamo model. So thank you.
Okay, I see first raised hand from co-host at IAA. Is there a question or general comment?
Yeah, I have a question. Hi, Bhuguti.
Hi.
Yeah, you shown that bimodal peak of this bimodal regions. Right?
Yeah.
That if you see the second peak, that corresponds to the bimodal regions without sunspots, right?
With sunspot. Second peak, this that is around 2 kilogauss.
Oh, that is with sunspots.
Yeah.
Okay, I just got confused. Yeah. Then it's fine.
Okay, I think first Sami had typed question/comment, so maybe
yes, yeah. No, that's where I'm going. Sami, please ask your question.
Yeah, hello Vibhuti. Thanks for that interesting talk. I was wondering if you are aware of the work of Karen Harvey.
I'm not able to recall that book.
Okay, because she did a huge amount of work on distributions of bipolar regions, including their tilt angles, etc. And she clearly distinguishes between active regions and ephemeral active regions. I think I was confused by your talk because you never use these terms, which are the standard terms. And my guess is that the blue distribution is what Karen would have called ephemeral active regions. Is that correct?
Since like ephemeral region, we have not isolated we have not followed the Hagenaar has used the first time definition, I guess, for ephemeral regions from the MDI data. So since we have not followed that definition, so that is based on the flux. So since we have only looked for the bipolar.
Active regions are defined as regions with sunspots, and ephemeral regions are bipolar regions, and there is a flux because yes, there are flux boundaries, especially lower one, not so much the upper one, but to distinguish from internetwork fields, etc. But you don't see internetwork fields in MDI anyway. But okay, that's the side point. I would suggest that you have a look at Karen Harvey's work, especially her PhD thesis, because a lot of this turnover that you see in the tilt angle is she finds basically because the smaller regions don't have such a clear tilt angle distribution. More and more random as you go. Other ones because local turbulence, convection, whatever, this is my conjecture, is going to have a bigger effect on these small flux tubes as they are rising.
Yeah, I definitely look at that work.
So I see more raised hands. That means very interesting discussion. Divyendu, if you have a short question, please ask. Otherwise, we will move the discussion to Slack.
Now, I just wanted to quickly ask whether, the tilt angle, of course, evolves with the lifetime of the active region when it's emerging and then relaxes to some particular kind of Joyce Law tilt angle. So at what phase do you determine the tilt angle? And do you use the same criteria of this phase for determining the tilt angles for all the regions in your set?
Yeah, because in this work, particularly the tilt angle is not like for a single bipolar region, like since in the 2 magnetogram, the same bipolar regions are present. So I have considered both the bipolar region as a separate bipolar regions, not as a single. So that's why I am currently working on that parts where I can track the bipolar region and then at some particular point, I can calculate the tilt angle. Like as you mentioned.
So in other words, you don't know at what phase you have got the tilt. You just have got it randomly at whatever phase.
Yes.
Okay, now I request Bibhuti to unshare his screen. And there are other questions. Please type them in chat and the speaker will engage there. And now I request Professor Solanki to share his screen and talk about the physics of solar irradiance variations. Sami, I will give a 20-minute mark.
Unmute. All right. Yeah. Okay. So good morning for those in Europe. Good afternoon for our Indian colleagues. I'd like to tell you a little bit about the physics of long-term solar irradiance variation. It's a pleasure to have been asked to talk at this important anniversary of the IIA, and I wish the IIA another 50 years of as big success or even bigger as it has had. Okay, so this talk is together with Natasha Krivova, my co-worker over many years. Now, irradiance, solar irradiance is of some interest to solar physics, but it's of much bigger interest to another and much larger community in physics, and that's climatry, as it's the biggest input in energy to the Earth climate system from anything, right? The other big natural input is volcanism, and then there are man-made stuff these days, but historically solar irradiance has been the biggest input. In recent years, solar irradiance variations have also become increasingly interesting for stellar people doing cool star research. Ever since the Kepler space mission of NASA produced data of almost equal quality as you can get for solar irradiance, people found for hundred thousands of stars that they show variations which can be very similar to the sun, but partly also very different. So that raises new interesting possibilities. But today I'm going to stick just to the sun. Measurements of solar irradiance with sufficient accuracy to actually see reliably changes in it started in 1978. You have to go to space to do that because the variations, especially in total solar irradiance, that means integrated over all wavelengths, are small, about 0.1% or so. You see the chart over here, where in color are measurements by different instruments as a function of time. Year is at the bottom, and at the bottom, the black dots are sunspot number for the same period of time. You see the solar cycle there. You also see that although measurements were almost uninterrupted, however, the different instruments have been more than 10 different instruments that have done the measurements. They show differences from each other, and cross-calibration between them is pretty challenging. The magnitude of the long-term change, long-term meaning longer than the solar cycle, is quite uncertain, and even the sign. So what you see here in this plot, this is based on work by Thierry Dudok-de Witt and co-workers, are three different reconstructions or combinations of the measurements from the various instruments. These are the three colored curves. And the green shaded area shows the uncertainty. 1 sigma, only 1 sigma. So, there's a large chance that the reality is lying somewhere between these within this green shaded area. And if I compare the minimum of around 1985 with that of 2009, irradiance could have decreased or it could have increased in that period of time. It's uncertain, even in this period where we have the measurements. And also a problem, especially for climate studies, is the limited length of the time series. So we have 43 years. That is quite a bit. It's a few cycles, but it's short compared to the period of time that we need to know what irradiance was doing in order to judge its influence on climate on Earth. So we need to, we need to find out the physics, what causes irradiance variations, and we need to be able to compute them, to reconstruct in the past, and one day, we are not yet there, maybe also predict into the future. In this plot, I want to show which physical processes are acting at which timescales. So this is a global wavelet power spectrum of the entire 43 years, or well, this was done in 2016, 2017, so it's a bit less period of time that we have measurements. And you see there is one very clear peak that's at 11 years. That's the left dashed line. There is another peak, which is actually not so clear in this, if you plot things in this way, but is clear if you look at rotational variability of solar irradiance. And that's the dashed line in the middle. That's at 27 days. That's at the solar rotation period. The whole thing covers something like 6 orders of magnitude in periods or frequency, period at the top, frequency at the bottom, and something like 8 orders of magnitude in power. So which are the physical processes acting there? So there is a small peak right out on the right which is at 5 minutes. That's due to the oscillations of the sun. The global modes produce this. Remember, in irradiance, we are integrating over the solar disk. After that, granular convection. Other convection may be also, but it's mainly the granules, which are dominantly the granules, which play a role till about 1 day, although individual lifetimes of granules are shorter, much shorter than that, but still they have an effect till about 1 day. And beyond that, it is dominantly the magnetic field at the solar surface, which is producing this. And this magnetic field, it's on the one hand, the sunspots, which are dominating at the 27-day period, but the faculae, the plage, they also play a role there, and that's why the peak due to the sunspot, that's one reason why the peak due to the sunspots is not so prominent. You also have faculae, which are dominating at basically all longer periods than there. They actually even start there where the sunspots are and go all the way through. And they certainly dominate on the 11-year period. It's not just the faculae, it's the network, enhanced network, which changes over the cycle, and that leads to this long-term variation. And you can use this information now to make models of how the irradiance of the sun should be changing. Now, granular convection doesn't change that much, so it's hard to predict what's going to happen on these short time scales. They're also not that affected by over the cycle, etc. These are, as I said, short time scales, and granules come and go in a turbulent manner, more or less. So we concentrate in the modeling on the longer time scales, which are also more interesting for climate studies. So you need to account for spot darkening and facular brightening to reproduce irradiance on timescales of a day and longer. For that, you need the coverage by spots and by faculae. You can do this in different ways. For spots, you can take the images in white light of the sun if you have them. When you go much further back in time, you only have sunspot number or sunspot area globally. If you go even further back in time, then you have to start using the cosmogenic isotope results that Hidya was presenting, or the sunspot number derived from there. For the facular brightening, as long as you have magnetograms, you can use them. More recently, there has been work to use, for example, calcium images, and I'll tell you a bit more about that in a few minutes. And as you go even further back than that, it starts to get problematic, and you have to then somehow use relationships between spots and faculae to do that. So that's one half of what you need. The other half is you need to work out what the spectrum will be. What is the contrast between spots and the quiet sun at wavelengths from very short to very long, because you need them all for total irradiance. And also you need to know spectral irradiance. That is pretty important too. And the same thing for facular brightening. For that, the best models, like for example, the Satire model that we use and one or two others, they use 1D model atmospheres from which the spectrum is computed. And combine that with the distribution to work out what the total brightness is going to be. And they do reasonably well, but there are a couple of free parameters in there. In particular, one has to scale the computed irradiance to make it agree with the measurements. So a couple of years back, we expanded on this, introducing what we call Satire 3D. And this makes use of, instead of 1D model atmospheres, we use 3D model atmospheres, such as you can see on the upper left. Sorry, the one movie has stopped working. One movie shows the vertical magnetic field, the other, the continuum irradiance, or sorry, the continuum brightness or intensity coming from 3D MHD simulations. made with the Murray code in this case. And you can make these computations for various amounts of magnetic flux, from quiet sun all the way to very strong active region flux, large flux, for example. And you can then compute the brightness. And using this approach, I don't have time to go into details, you can get rid of that free parameter. You don't have to scale the irradiance measurements, the irradiance models to the measurements. And the result is shown on the upper right, where from the period from 2010 till 2017, you have in red measurements by the total irradiance monitor on the source spacecraft, the TIM, shown in red, almost covering a solar cycle, and in black, we have the reconstruction using this model and the magnetograms from HMI and the continuum images from HMI to get the coverage, but the spectrum is got from the MHD simulations. At the bottom of that figure is a blow up, and you can see the agreement is remarkably good. We can reproduce 98% of all the variations in this time scale between a day and about a decade. This leaves very little wiggle room for any other physical processes except the evolution of the magnetic field at the solar surface for producing solar irradiance variations. Okay, now this is on timescales, from days to decades. What about if we go further back in time? Because this period was just to find out, do we understand the physics of what is going on? As you go further back in time, we don't know if there are other processes turning up. And indeed, people have used very, very different, usually, in most cases, extremely empirical and extrapolative work to work out how strongly solar irradiance changed. For example, since the Maunder minimum, right? The Maunder minimum was in the second half of the 17th century, let's say from 1650 till 1710 or so. And here are different reconstructions of the irradiance and different estimates of what the irradiance was at that time. And you can see that they differ by an order of magnitude. Right? The green curve is, half a watt per square meter less, or 0.07%. The light blue curve is 6 watts per square, or more than 6 watts per square. So a full order of magnitude. Who is correct? Right? If you take the green curve, then most climate scientists will say, well, that has a very small influence on climate, on historical timescales going back, further back than the 20th century, and the sun was totally unimportant in driving climate over the last millennia and hundreds of thousands of years or whatever. Whereas if you take the blue curve, the light blue curve, it suggests that the sun was really dominant. It had a huge effect. So who is correct? We decided to take a very different approach because we now have a model, the Satyr 3D, which doesn't have any freedom, doesn't leave us any freedom to tune parameters. We said, okay, what could be the state of lowest activity of the sun? We know that there is a global dynamo working in the sun, which produces active regions, but we also know that there is something like a small-scale turbulent dynamo acting in the convection zone, including at the surface, and it produces a lot of very small-scale mixed polarity fields. You can see that in these images now. Sorry, the movie stopped working. On the left, brightness, which basically shows granules. On the right, you see the magnetic field. It's an artificial magnetogram produced in this simulation by Matthias Rempel from 2014. You see granular scale, larger scales, but the fields are on the whole not very strong, and they're mixed polarity. Some of them become strong, but mostly they are weak. We know from observational work that this local dynamo is invariant with time. It doesn't follow the solar cycle. And we think it maintains the field even if the global dynamo is not acting. So in that sense, the magnetic field, the state of weakest activity of the sun that you can have is when the global dynamo switches off completely and you only have the small scale dynamo acting. I'm not saying that this actually happens, but this would be a lower limit to the activity. And it turns out it's also a lower limit then to the irradiance of the sun, to the brightness. And this is an approach that was taken by Yu et al. Last year. And they could set a limit on how much darker the sun could be during the Maunder minimum. They said it could not get darker than 2 watts per square meters, 2 plus minus 0.7, below what it was during the last minimum in 2008. And this is now overplotted again on the same figure as I had showed before. The white part at the top, that is allowed. The red part at the bottom is not allowed. And it's clear that the blue curve and all the other models and estimates that have been made of solar brightness during the Maunder minimum, based basically all on the same technique, they're not allowed. And we also have understood why that is so, where the mistake was made when reconstructing those blue curves, etc. As a solar physicist, of course, we would have preferred to have the sun being the dominant driver of climate, but it turns out that this limit restricts the role that the sun could have played in driving global warming and also climate change at earlier times. But I think the last word, in this case, I don't think we are going to get the sun varying much more than that. But there may, on the climate side, I think there are still quite a few things that could be done, feedback mechanisms, etc. Okay, let me move on quickly to talk about calcium K archives. Now, as I said, direct measurements of irradiance started in '78. Regular magnetogram recordings of sufficient quality also started in the 1970s. Before that, you only have sunspots to reconstruct irradiance. That's what's been used so far. Yeah? And that's not ideal at all, because we know that the long-term changes in irradiance are due to the bright component, due to the network, due to faculae. And you have to deduce them somehow using the sunspots. And you can only do that by assuming that earlier cycles behaved the same like recent cycles, and there's absolutely no guarantee that that was the case. Now, since 1892, there have been measurements of calcium K images, usually spectroheliograms in the old days, more recent times with CCDs and improved filters. These have been filtergrams, but for most of this period of time, these are spectroheliograms. And these observatories are distributed all over the world, including, you can see, a very famous one at Kodaikanal. Now, people have been using these data in the past, and they have reconstructed irradiance, but there have been some issues with those. They have either used the CCD-based data, which is fine, you can do that, that's good, but it doesn't help you, it doesn't go back very far in time. Or you can use the photographic data, and people have generally used uncalibrated photographic data, which is dangerous. Yeah, because photographic plates, they are nonlinear, and calibration is extremely, extremely important, but also extremely, extremely difficult. Also, generally single archives have been used, usually the Mount Wilson archive, which is now highlighted in black. There is also the Sac Peak archive highlighted in black, which is at that time was a CCD based when it was used. But we have lots of other archives. For example, Kodaikanal, which I've highlighted now also in black, this period of time, starting in 1904. which has not been used very much for reconstructing irradiance. And what had not been done so far is to study the effects of the difference between archives, right? In all, there are 38 archives known, 300,000 images approximately. And if you look at the coverage from all the archives, all the images you have actually got a 98% coverage since 1907. I mean, that's fantastic. But these are different archives having different problems, different calibrations, etc., etc. And that has to be taken into account.
Sami, 3 more minutes.
3 more minutes. Okay, let me try. You can go and correct. On the left, in the left image, on the left, you see the original data. On the right part of the left image, you see final masks of the plage. Theo Katsistergos, who did this work, did a fantastic job. He also combined the data from all the archives to produce a composite together with many authors from all these different observatories with an uncertainty that's plotted on the right. The colors show sort of the level of the uncertainty. You then convert the calcium brightness into magnetogram signal, unsigned magnetogram signal. You can do that. There is a nice relationship between the two, which has been known for a long time, but you can do that with the historical data also to calibrate them. And finally, you can use these unsigned magnetograms using, again, the satire model that I described earlier and reconstruct the irradiance. And so first tests have been done using calcium images, CCD-based calcium images shown on the left. And the results are incredibly good. You get something which is not quite, but almost as good as when you take the magnetograms directly. And on the right, this is very first results for a photographic archive where you also get surprisingly good results. This is for relatively recent times with the Meudon, but this will be extended back in time and improve irradiance reconstructions going back hundreds of years, or at least for 100 years. Okay, let me just say a few words about solar spectral irradiance. And that is important. I'm saying this basically because of the upcoming Aditya mission and the suit instrument on it. There is a huge discrepancy between models and the only observations between, or very few observations between the 200 and 400 nanometer range. That means in the near UV. The models say that this part of the spectrum is responsible for something like 30 to 60% of the variations of the total solar irradiance. The observations with the SIM instrument on source say it's well over 100%. And you can see that why this is so in the image on the right. The model says, okay, and in the visible and infrared part, you have the same sign of the variations. That means the sun is brighter at times of activity, of high activity, as in the UV. The SIM measurements say, no, the sun is a lot brighter in the UV at activity maximum, but it's actually also a lot darker in the visible at activity maximum. And we don't know who is correct. Both are very difficult things to do, the models and the measurements. And the important thing is that if you take the blue curve or the black one in this figure, you get totally different effects on the climate. And this is due to the top-down modeling. I have no time to go into that. And Aditya will be well placed to resolve this because it doesn't have to make use of uncertain non-LTE modeling like the models have to, and it doesn't need to have absolute radiometric stability because it's resolving the sun for the first time, giving us images broadband between 200 and 400 nanometers. That'll be very, very exciting to get these results from the suit instrument. And if I still have a minute, just the very long term, Ilya Uzovskin in his talk very nicely showed the reconstruction of activity of sunspots based on global carbon-14 or on local 10 beryllium archives. You can then use those sunspot numbers to reconstruct cycle averaged. Okay, at the moment, only cycle averaged irradiance on these very long timescales. What you see is differences between grand minima, periods of normal activity, and also grand maxima, although for the irradiance, it actually turns out that grand maxima are not much brighter than times of normal activity. This is because sunspot area increases much faster with activity than fecular area does. So that sort of tends to level things out a bit. And that's where we stand at the moment. The next step will be to use these beautiful data produced by Brehm et al., the yearly measurements of carbon-14 over the last 1,000 years, and the work that Ilya and others have been doing very, very recently to turn that into sunspot number so that we can reconstruct the cyclic irradiance over the last 1,000 years. And that'll be very exciting. Thank you very much.
So thank you, Sami. That was a very comprehensive overview. Now we have time for a couple of questions. If anybody, first question goes to Ilya, please ask.
Thank you, Sami, for the very good talk. I have a very short comment and a very short question. The comment is that we do know that during, in particular, the Maunder minimum, the large-scale dynamo was not completely off because there was still a modulation of cosmic rays, but as an assumption, that's fine. And the question is, since you said that no free parameters is in the new 3D model, can it be used to calibrate the instruments, as you mentioned in the very first slide?
As far as I'm concerned, yes. But you have to convince the people who built the instruments, right? I think no experimentalist or observer wants to calibrate his or her instrument against a model. It should be the other way around. And there is still, there is no free parameter as far as the magnitude of the variability is concerned. But we cannot get the absolute brightness of the sun out of this model, because for that we would need to know exactly how well the fusion is working within the core of the sun. And we need to know the history of solar activity over the last 100,000 years. That's a relaxation time of the convection zone, right? Which we don't. So we cannot give this absolute value. So the absolute value is uncertain. That we cannot do. With the variation, we don't have a free parameter.
Okay, so the next question goes to the coordinator of IAA. Please ask.
Oh, okay. Hi, Sami. That's great presentation. Thank you. This is Rajaguru in the IAA auditorium. So we know that the bright component, which contributes to the ones due to faculae and other bright structures, is due to a very delicate radiative transfer effect, right? It's a near surface structure, including opacity. All of that contributes. So I'm just wondering, in the field of stars, sun-like stars, how do we expect? Does the sun fit in well with what we expect from current observations? And
That's a very, very good question, and there is a huge debate in the community about that. And this debate goes back already 30 years now. In 1992, when people showed that over the solar cycle, the sun is much less variable than other sun-like stars. That debate has gone away a little bit in recent years because there were a couple of simplifications that those people had made, which in the meantime we know were not so good. But very recently, last year, there was a paper in Science by Reinhold, Timo Reinhold et al., where they looked at the rotation timescale in Kepler data of solar twins. And they showed that the variability of stars which have the same effective temperature, the same log G, the same metallicity, and the same rotation period, right? So they are, for all intents and purposes, solar twins, that many of these stars actually show much, much larger rotational variability. And we don't understand what's going on. So could it be that there is something in these stars which is different, which we just cannot tell from the information we have? Or could it be that on very long timescales, this is longer than 10,000 years, because we don't see any signal of this in the cosmogenic isotopes, could it be that also the sun can go into this ultra-high variability, which generally also means ultra-high activity state, that the dynamo flips into a totally different mode? We don't know, right? So that's an open question.
Okay, so thank you. If there is time, the chairs, can I ask one more question?
Please hold on. There is one more question in chat. First, I will ask that, and then. So, Sami, what's the peak? Maybe a slight one between 100 and 1,000 days in the power spectrum of irradiance variations due to. Is it significant? That's a question in chat box.
Right.
For me. So I wrote that question. Sorry. Yeah.
Yeah. Okay then.
Okay. Yeah, I'm trying to get back to there. You meant this one here, right?
Right.
The peak between. Yeah. It's not absolutely clear. This is at around a year, 1.5, something like that. And it could have to do with surges to the pole, where you have, the decayed active regions, their products. So it produces a lot of faculae, which are distributed over a large range of latitudes. But actually, it isn't clear.
Okay, thank you.
And there is, the peak is, it looks like a peak, but actually there is a bit of a depression here.
Yeah.
You can also interpret it like that, right? That this is just something that is going up, and there is a depression here. It's hard to say.
Yeah, okay, thank you.
Okay, Shushant Mahajan, would you like to ask a short question?
Yeah. My question is of the energy, excess energy that comes when solar irradiance goes up. Do you expect that to come entirely from magnetic fields? And eventually it has to come from the core, but is magnetic fields the previous step to solar irradiance modulation?
Well, indirectly, not directly. It is not magnetic energy per se. Right? Magnetic energy per se is much too little. What it is that the magnetic fields, sunspots in particular, will quench, or also the small scale kilogauss fields will quench convection within them. So you will get less energy coming up. That is why sunspots are dark, basically. Yeah. And this energy gets redistributed within the convection zone. This was something that Hans Freud showed already 4 decades ago, and will come out over this 100,000 years, which is the relaxation time of the convection zone. Right? That is what leads to these dips in brightness. On the other hand, what the magnetic features also do, because you have an excess pressure in them, the magnetic pressure, they produce a dip in the solar surface. That means they increase the size of the solar surface and they move it down into layers which are a lot hotter, because the temperature rises very, very rapidly as you go into the sun. And that's where you get additional radiation that can seep out, can be radiated, right? A bigger star is a brighter star. And so you have increased the surface of the sun. and you have made it a little bit hotter because you're sampling deeper layers, and that's where this excess radiation comes from. But again, it is coming from the whole convection zone, and this is going to thermalize again and relax in these 100,000 years.
Awesome. Thank you so much.
So thank you, Sami. And I do not see any more questions. At this point, I see that there is a lot of lively discussion happening related to the tilt angles and the emergence of active regions. If everybody is on board, I would suggest that we will spend maybe 5 more minutes because this is the last talk of the session and we have time. I also cut down many questions in the previous talk. If anybody has any burning question or would like to make a point, we will do that now for 5 minutes so that everybody can participate in the discussion. Please raise your hands.
Okay, I should raise my hand first. That's right.
Okay, yes, you roll. So okay. Please talk.
This is back to Sami actually before we get to Vidya. So this is a very intriguing question on whether the sun is unique or whether the sun is just another solar-like star. So when you say that that there's this evidence that other solar-like stars are more highly variable than the sun, could there be a systematic that I can only see this variability in faraway stars if they are high, and so I'm therefore collecting data from stars which just are highly variable, whereas the others are where the variability is less. We are getting and solar-like stars, we are missing them out. Is it a possibility?
Oh, very much so. Yes, yes. So biases are, of course, in stellar astronomy, they're the bane of people working in that field, and you always have biases. And there is a bias here as well. So there are, in the Kepler sample, there are something like 300 something solar twins, right? But at the same time, there are also thousands, forget exactly which number, but maybe 2,000-3,000 stars which are near pseudo solar twins in the sense that they have the same temperature, everything else, except the rotation is not known. Okay? So you don't know the rotation, but if you take the normal methods of determining rotation on this and you apply them to the sun, it only works at activity minimum. At activity maximum, you will not get the correct answer, okay? Or you will not get any reasonable answer. So what we think is that, this is pure speculation, right? That many of these stars are like the sun, and they're probably even the majority, and that the sun would in that sense be normal, but we can't say because we can't determine the rotation rates of these stars. The stars you can determine the rotation rate are the ones which have a very regular cyclic, where you have either huge star spots or the star spots live very long, or you have some kind of, what do you call them? Fixed latitudes, where you have these star spots, active latitudes or active longitudes, not latitudes, sorry, yeah, active longitudes. But the question still remains, are these stars which are different from the sun? Or could the sun 10, 12, 15, 20% of its time move into such a state? Then it would have a huge effect on Earth.
True. And if you look at, now tying everything together, if you look at Ilya's presentation and this idea that when you look at the GAN maxima phases and then the normal activity phases, it seems to be drawn from a similar sort of statistics. The PDF looks similar and they're overlapping. Then it is very likely that the sun could kind of shift between this very high activity mode and normal activity modes with very occasional Maunder-like minimum. That's a distinct possibility.
It is a possibility. As I said, we don't know, right? But some of these stars show variability, which is basically an order of magnitude larger than the largest we have seen in historical times, right? That's worrisome. You don't want to know what kind of flares that would produce, for example.
All right, thanks. I think that was a very interesting session. I enjoyed your talks.
Thank you.
I can give a just quick comment on that. Like, of course, I mean, I did not know about the differential rotation of that star, but there is one idea, I think a few years back came from Excel, and then I wrote another paper. The idea is that if a star has anti-solar differential rotation, then that can produce huge magnetic field. I mean, much stronger magnetic field that we expect of the same type of star if the just differential rotation is anti-solar. I mean, it's just an theoretical idea, I mean, based on the dynamo. But as we know, we have very limited knowledge of anti-solar differential rotation.
It's not clear how much more active those stars actually are. They are much more variable, but if you take all the sunspots you have and put them into 2 active longitudes, you will get much larger variability by a factor of 2, 3, 4, without actually needing to go up with the activity level too much. And the question is also something we don't know, right? If these stars have hot Jupiters around them or brown dwarfs in close orbits or whatever, which could produce something like that. But there's a lot of speculation here.
Okay, so I hope everybody had a chance to ask the question, and Rob has a point or would like to comment on something. Rob, would you like to ask yourself? Okay. Yeah, please go ahead.
You see it in the chat. But so the point is that, yes, indeed, the sunspots are dark because they quench convection, as you said, and the energy got redistributed in the spread way. But in the UV, you got all these small flux tubes in the network and plage, and they are bright in the UV continua. Also because of sprout, because there are holes in the surface that leak from sideways up. And so there it's a little bit different.
Okay, so I think there is a more general question that any expert feels like they can respond in the chat, or is it particular to Sami or any of the other speakers? Okay.
So, I was trying to make a point for Bibhuti and Vidya in the chat. Maybe, since there is nothing scheduled right now, and this is a very interesting topic as well. Can we maybe have a short discussion on that?
Of course, that's the whole point. So please go ahead and make your question short or something like that, and then we will have a longer discussion.
Right. So this is regarding the tilt angle variation with flux. So I have referred to a paper here in the chat box. This is a paper by R.F. Robert Howard of Howard, 1996. Please go ahead and look at figures 2 and 3. He does the tilt angle variations with flux, and you see this evidence of what you call quenching, but what is also understood to be, because, flux tubes rise faster, bigger flux tubes rise faster, and therefore have, pick up less tilt, right? To conclusively show that you are finding evidence of quenching, I think you need to sample the same type of active region and show that there is a turnover in the tilt. There is a high probability that you are actually sampling 2 different populations, and the turnover that you see are basically 2 different dependencies of the tilt in 2 completely different populations. I think this is the point that Sami was also probably trying to raise or allude to earlier.
Yeah, just to add, so I mean, I know this paper, I mean, after you refer, of course, and then there's another paper where Sami is also co-author based on this same Maud-Winson data and Kodaikulan data. So the previous work by Howard, they use the sunspot group data as well as the plage. And then this paper from Sami's group, they use the sunspot data, white light data. So all these, of course, find some magnetic, not magnetic field is there, some sunspot area dependence and flux dependence. So what we tried to check that, okay, let us see the bipolar magnetic region. Just clearly we'll define the BMR. and we'll see what variation we see within a cycle. Okay, so we got some trend, okay, but not conclusive. I mean, we did not say, probably like Vibhuti did not we did not say that we got a strong evidence. It was just a hint for the Tiltquenching. Still, it is not very conclusive. I mean, I agree with you, and we need to track the BMR, and we should make sure that we are taking the BMR at a particular phase, okay, so that there should be no dependence on its evolution.
I would just like to add.
Yeah, I know. So just one add one.
This plot,
I'm very excited to see the tilt of smaller guys like ephemeral region. And I was for last few days, I was actually studying all the literature, and I also now started analyzing the ephemeral region. So the earlier literature says that there is very little or almost no dependence, no Joyce Law in ephemeral region. And then there's another paper by Tiltquenching and others. They show that they find anti-Joyce law for ephemeral region are even smaller than ephemeral region. So at least in our study, I mean, we are very sure, not maybe 100% sure, that we do not include those smaller guy, because all features actually do so statistically Joyce law. Okay, that's what we can say.
Hi guys, Bidya, just a quick note. So we will take a break for 20 minutes, I think. You can continue discussing, and those who want to take a break, do take a break and come back at 4 o'clock. So the next session will start at 4. So you go on, you can go on discussing. But those who want to take a break.
Before everybody leaves, I would like to thank all the speakers for leading a very good discussion, and also all the participants for a lively discussion, and my co-host Nishant Singh. And yes, please continue discussing. Thanks.
I should probably apologize. Without the permission of the chair, I shared my screen.
No, that's
it is just an informal discussion. I thought it will be easy.
No, that's perfectly fine. Yes.
Okay, thank you.
Yeah. And thanks to the chair, who did a very good job of keeping even someone as disorganized as me on time. That's something.
You were giving a very passionate talk about the calcium index. I didn't want to stop, so I gave 3-minute mark instead of 5-minute mark.
Thank you, Chaz. Yeah, thank you. I would request the next session, Chaz, to be kind of online and take care of the next ones.
Okay, just to add, Bidya, Dibyendu, yeah, this
now invite Mats Carlson for his talk on modeling the solar chromosphere. So over to you, Mats. Thank you.
Thank you very much. And it's very nice to attend this very well organized virtual conference. So I will talk about modeling of the solar chromosphere, and I apologize for the ones that have seen some of the material before, but there should be some new stuff. So the first question is, what is the chromosphere? And the name says it all. It's from Greek, chromos, and sphere. So it's a colored sphere that you can see in a total solar eclipse. That is the origin of the name. And the color comes mainly from H-alpha radiation. And it was clear early on that you couldn't get a fit to the observations with a standard radiative equilibrium model. So if the temperature sort of falls all the way, then you would not get what you observe. And then the first modeling was to do semi-empirical modeling. And the maybe most famous one is from Vanessa Everett-Löser and their third paper. And their model, they have a series of models, A, B, C, D, E, F, and the one that fits sort of the average sun is the C, Val3C model. So they then treated the temperature as a function of height as a free parameter in a one-dimensional plane parallel model. And then that was modified by hand to get as good as possible fit to the diagnostics. And I've tried to show in the cursor here, it's indicated in this figure. So it was mainly based on continuum observations in the ultraviolet. So you have the continuum shortward of 168 nanometers or 1680 angstrom coming from an excited level of silicon. And then you have another continuum where the opacity is dominated by silicon and from the ground state. So, and then a carbon continuum around 1100 angstrom. So these observations then constrained the temperature structure in a model. And also they used some millimeter observations to constrain part of the upper chromosphere, but mainly then the Lyman alpha line in the wing and the Lyman alpha line center. So these calcium K line, magnesium lines were not really used to constrain the model, but as a check of the model. And also then to modify the model because the calcium K1 didn't really fit very well with the model. And they needed to have a plateau in order to reproduce the Lyman alpha intensities. And then the region from where the radiative equilibrium, the temperature falling ends, the temperature minimum around 500 kilometers, and up to where you have a very steep temperature rise in the transition region was named the chromosphere. And often it is regarded, or people talk about the chromosphere as being a layer between around 500 to 2000 some kilometers. And I think this is a wrong way of, a wrong frame of mind to explain the physics that goes on, to regard it as a layer. And we talk about the coupling between layers, and I think that's also then put your mind in the wrong framework in order to understand what's going on. As we'll see, it's very dynamic, it's very structured. So instead, one should ask, what is the physics that really sets this region apart? And well, one can see here that we have a temperature falling, and that's because it's dominated by radiative flux being the energy transport mechanism. And when that's not true anymore, we have some input of energy, we can get a temperature that increases. So the chromosphere starts where you have a dominant non-radiation part in the energy equation. And then when the temperature is high enough and hydrogen starts to ionize, then you can't cool this or balance this energy input. So it goes straight up. So it's really the region where you have a non-radiative energy input and hydrogen mainly neutral, which is the chromosphere. So why is it important? Well, heating and mass balance of the corona has been a big question, a big task to try to come to grips with for a long time. But the heating of the corona, the energy and mass has to go through the chromosphere. And actually, because of the much higher density in the chromosphere, you need 10 to 100 times more energy input to sustain the conditions in the chromospheric material compared with the corona. Also, the chromosphere is where the gas pressure and the magnetic pressure balance are about the same. And that means that deeper down, it's the gas or the plasma that dominates and forces the magnetic field to move around. While higher up, it's a magnetic field that dictates what the plasma should do. And the transition happens in the chromosphere. It's also about the same place where the Alfvén speed and the sound speed are equal, so the waves don't really know what they are, and you can get a conversion from one wave mode to another. So then why is it difficult? Well, one reason is that we do not have that many diagnostics available from the ground. And of course, it's much easier to observe the sun from the ground than from space. Basically, we have the H-alpha, the calcium resonance lines, and the helium 10A30 line available from ground. And they're all a bit difficult to understand in terms of their formation. They're optically thick and they're dominated by departures from LTE. So we have a lack of diagnostics from the ground, we have difficult diagnostics and also complex physics. Already we cannot use LTE, local thermodynamic equilibrium, to do the radiated transfer. We have many scale heights in density going through this region, and we have small and large spatial scales that couple. And also the densities start to get low enough that we don't have enough collisions to couple ions and neutrals. So they start to decouple, and you've heard that before in this conference about ion neutral, that you have to take into account the effects between ion and neutrals and that they are not completely coupled. So what does it look? If we look at observations, it's always good to use observations as your guide for what the reality is. And H-alpha was one of the diagnostics. So this is a picture taken with the Swedish 1-meter solar telescope on La Palma. This is the mean profile, and this is the transmission profile of the Fabry-Perot filter of CRISP. And then you can move this, you can tune it to any position, and then get different pictures. Here we have enhanced what's outside the limb to see it more clearly, otherwise it would be almost dark. And if we now scan this line, we see that in line center, the opacity is much higher, and we don't see through at the limb anymore. And just in this image, we can see that the difference from the line wing to the line core is by 5 arcseconds, so 3.5 megameters, much more than this 2,000 kilometers in the Val3C model. And if we look at a movie taken at the line center, we see all sorts of dynamic features, these dynamic fibrils and other features here, they're moving in time. They're structured. We have coronal rain, so we have some cool material visible in the H-alpha line center, high up in the corona as well. This is another picture taken in the H-alpha showing the fantastic amounts of detail and detailed structuring we get from the magnetic field up in where the magnetic field dominates the behavior. This is the picture from a 1D semi-empirical model. So you can compare, this is the chromosphere, this is what a 1D model would predict. It's all homogeneous. So of course, it's obvious that that's not a very good picture. So what can we do? Well, we have in Oslo worked with a code called Bifrost, and there are also other codes capable of doing modeling in 3D, and you've heard of some of them earlier. This has been designed specifically to deal with the special physics of the chromosphere. I won't go through all the details here, but what is a bit different from most other codes is that the radiated transfer takes into account scattering, which becomes important in the chromosphere, and also non-LTE losses in the chromosphere, while optical thin in the corona is much easier. to take into account. Conduction along field lines is important if you aim to also include the corona in your simulation. These last bits are modules that you can switch on and off. When you switch an arm on, it takes between 3 and 10 times more computing time. So most of the time for this, we're still in the exploratory phase, looking at what magnetic field configurations are really doing what. So these have normally been switched off. And then the simulations, we simulate only a small part, a box in a star. So a typical simulation is 24 megameters on the side and going down 2.5 megameters and up 14 megameters into the corona. But we have a box then that include the top of the convection zone, the photosphere, the chromosphere, transition region, and the lower part of the corona. So I'll look or show some simulations, actually 3 different simulations that all have this characteristics of 24 by 24 megameters going down 2.5, up 14.3, with a spatial scale of 31 kilometers and a vertically 12 kilometers as a minimum. It's a varying spacing vertically. So the free parameter here, we only have a small part, so we don't have a consistent description of how the magnetic field is formed, except that we have the small scale dynamo in our upper part of the convection zone. But apart from that, we don't have the larger scales of the magnetic field specified by ab initio. So we have to put that in. So that's a free parameter. So these simulations, they differ in terms of that free parameter. One, where we put in 2 main polarities, opposite polarities, 8 megameters apart, but a balanced field. So the average is 0. The average sign field is 0. We have a quiet sun where we only have the small scale dynamo field and we don't have any imposed free parameter large scale field. And then the average unsigned field in the photosphere is 39 Gauss, which is on the low side or quite a bit lower than what we believe is true in the sun. And then we have another simulation, which is a quite some simulation, but a 2 Gauss vertical field on top of that. So this is the enhanced network. We see the 2 polarities, the negative and the positive polarity, and we see that it has already been swept to the intergranular lanes. And the maximum field strength here is about a couple of kilogauss in these concentrations. So we can expect to get some connections between these polarities. And if we look at how the temperature looks like in the chromosphere, then we can do that with the volume visualization. So here the blue is one polarity, red is the other polarity. So we have the magnetic field in the photosphere. And then here in the volume visualization, we have the matter at a given temperature. So that we start here at 5,000 Kelvin and what plus minus something. So a log temperature of 3.7 and how that is distributed. And we can see that when we go up to about 5,600 Kelvin, we see small loops, short loops. So the higher temperature plasma is aligned with the magnetic field, or we can suspect that at least. And then we can check it with the simulation, and that is true. And when we go up in temperature now, 7,000, 8,000 Kelvin, that is more and more true, 20, 50,000, 100,000. And now at about 200,000, we get a new set of loops that are sort of more diffuse. Here we see at 300,000 and 800,000, and the high temperature we find actually in more compact loops in this simulation. And if we look at it from the side, and this is now the chromospheric temperature around 8,000 Kelvin, we see that it's also dynamic. In addition, we can see some global oscillations. We see things that are moving there. We have one, and that comes from the initial conditions not being quite consistent. So we have oscillations, but initially we have larger amplitude oscillations as well. And we see towards the end of this movie, we see also some eruptions happening. So we have one there, throwing a matter to higher heights. If we now look at these diagnostics that were used for the Val3C or that were indicated in the Val3C, we can see that, for instance, Here we have the calcium-2H core that it's formed here at this point in X. This is a cut through the simulation. This is at 2.5 megameters. Here it's at 1 and 1.7. So the height of formation varies a lot, depending on the density structure. We also have some other diagnostics, and typically they are ordered in the same way, that the 8542 line is formed deeper down than the calcium H, but not at a given height. And this is where we have the temperature of 20,000 Kelvin and 10,000 Kelvin indicated. And the magnesium H3, that is a good diagnostics used with IRIS, is the highest of these ones. In grayscale here is a helium-10 If we now switch to the quiet sun simulation, we see here the magnetic field, that it's much more salt and pepper. We have different polarities everywhere. And I'll return to that, but first look at the temperature distribution here. So as a function of height, this is the probability density function for the temperature. So here we have the photosphere with a rather narrow range. And when we get to where photons start to escape, there is much more of a contrast between the intergranular lanes and the granules. And then we get up to a temperature minimum. And here there is also quite a large range of possible temperatures. And we see 3 bands of preferred temperatures. And they will be explained later, but they are because when we have LTE ionization at this temperature and a rather narrow range of temperature, you ionize hydrogen. So when you compress the gas, instead of increasing the temperature, you just increase the ionization of hydrogen and the temperature stays the same, more or less. And this is from helium-1 and helium-2. And here we get up to the corona, and when we run in time, we see that the corona relaxes to a rather constant temperature because of the dominance of conduction. If we look at the quiet sun, this is started from a photospheric simulation and then an average model. And we see then when we start it, it cools down because we don't have any heating from the magnetic field related processes. But after a while, we do get magnetic field from the small scale dynamo to appear also up in the chromosphere and the corona, raising the temperature in the corona, but not to 1,000,000 degrees, but only to a few 100,000 degrees, because this is a balanced field, so we have very weak field up here. And this about the ionization. If we do not assume LTE, but solve the equilibrium equations for the various ions and get the non-equilibrium ionization, time-dependent ionization taken into account, these preferred bands, this is hydrogen, helium, helium, and then if we just do hydrogen non-equilibrium, the hydrogen band disappears. If we do also the helium ionization with non-equilibrium, all these preferred temperatures disappear. But it's very costly. The quiet sun simulation now seen from the side and chromospheric temperature in the beginning, we just had a plane parallel atmosphere on top, but very quickly we see that these waves really create this dynamic atmosphere. And towards the end, when we have some magnetic activity up in the atmosphere, you also get these swirls and larger scales reaching high up. I mean, this is 14 megameters. So this chromospheric material can be going up all the way to the top of the box. But you don't need much of a unbalanced field. This is now with 2 Gauss in addition to the quiet sun. And that prevents much of this activity. But you can see that you still have some here. So it's just suppressed, but it doesn't disappear all the time, all the way. So it is important, the magnetic field structure, which is unfortunately for us a free parameter, is really determining what's happening in the chromosphere. So how does this compare with observations? Of course, that's really crucial. And we have here, luckily, then space observations as well. So this is from Iris. This is a slit jaw image in silicon 4. It's part of it. So it's an enlarged image. And we have then magnesium 2, the K line, and the carbon 2 lines along this slit. So how does this compare with the simulation? Well, this is now the simulation, and you can see that even the 24 by 24 megameter is 30-some arc seconds, is very small compared with even this cutout of the slit jaw. So we can only do a very small part. But we have more or less the structures we have. This is with the same color scale. So we do have the brighter network things, and we do have dark between the network areas as seen in this silicon 4. This is a synthetic then slit jaw image. And here in the magnesium, we see also that we see the line is rather narrow compared with the observations, but it's has some similarities. And also here we have the carbon 2 line. Again, it's a bit too narrow. So this is now in showing the observed in the plage and in the quiet sun, and this is in one of the simulations. It's more or less similar in intensity, but it's too narrow. And again, the K2 intensity in a histogram. So this is now the enhanced network. So we have some really bright and we have some really dark features. So the range is larger than in these quiet sun observations in Iris and the plage observation. And the main difficulty here is that the K2 peak separation is a factor of 2 smaller than in the observations. So for conclusions, the chromospheric structure and dynamics, they're critically dependent on the magnetic field topology, and the interaction of the ambient and emergent field is important. We haven't shown that. We have some simulations also for where we look at element bombs and UV bursts, and they come from the interaction of the field that we put in the box. So what we have in the box is really crucial, and if we feed in strong field, we can get all sorts of activity. All spatial scales matter, and we have 2 narrow profiles. So the 2 narrow profiles, how can we solve that? Well, these are optically thick lines. We could have more turbulence, but there are other indications from optically thin oxygen line observed with the Iris that is not the case at least in the quiet sun, intergranular or internetwork regions. So then we need to do something about the source function. So we need a flatter temperature structure. So we need more chromospheric material. We need more, especially in the lower part. Maybe that is the lack of that, maybe the lack of numerical resolution. It may be that the neglect of ion neutral effects in these simulations play a role. And it could be also that the magnetic field history, we put in a field and we don't let it evolve. So in this enhanced network simulation, we put in these 2 separate polarities and have a potential field up in the chromosphere and higher regions. We don't let it come up carrying material with it. And that is something that takes a lot longer, but we are working along all these avenues. So thank you for your attention.
Thank you, Mats, for a very wonderful talk. Now the floor is open for questions. Yes, I see Piali. You can unmute and ask the question.
Yeah. Hello, Mats. Nice to see you again after a long time. Yeah, I had, can you hear me?
Yes.
Yeah. So I had one question about the coronal hole case that you showed. So there, I see that you imposed a magnetic field of 2 Gauss. So do you have any other cases where you experiment with higher magnetic fields, and how does it change the results?
Yes, we have one with 5 Gauss instead of 2 Gauss. And then we have some with 2.5, but it's basically 2 and 5 is the ones that we have experimented with. And they have share a lot of the same features, but in the 5 Gauss, you have even more suppression of sort of the wild activity we see in the completely balanced. And I think that if for a 24 by 24 megameter box to compare with observations, often you compare with much larger observational areas. So if you take a full Hinode field of view, then you have much more of the balanced field. But if you take a 24 by 24 megameter part of the Hinode, it's almost never balanced. So I think that it's rather artificial to have a completely balanced in a 24 by 24 megameter box. So I think that the 2 Gauss is more typical of what's happening in the quiet sun, not only in the coronal hole.
I see. Okay. Yeah. Thanks, Mats.
Pradeep?
Mats, thanks for a very nice talk. This is Pradeep Chita from MPS Germany. I have a question related to the detector maps that you displayed towards the end of your talk. So there is this striking continuum emission that you see in the simulations that is absent in observations. Now, is it because of the sensitivity of observations or is something additional going on in the simulations?
So is which figure?
If you go back. Yes, here.
Or here?
No, the next slide. Yes, here in the lower left panel and the lower middle panel, you see a lot of horizontal streaks which represent the continuum emission, right? Now that is not that obvious or not that prominent in the observations in the top panels.
I mean, part of it's a very interesting observation there. So, I mean, we are going through sort of these loops. So it could be that it's partly, well, I mean, you would see it similarly here, I guess. So no, I don't have an explanation. Part of it is the spatial resolution, so it will be smeared. But still, I think that if we did smear this with the PSF, spatial PSF of iris, we would still see a difference. Mm-hmm. So I don't have a good explanation for that.
Oh, that's good. Thank you very much.
Yes, Sami, you can go ahead.
Yeah, well, maybe just a comment first to this here. Isn't just the grayscale totally different in the 2 figures?
No, it's the same.
It's the same because my understanding was that you have the magnesium profiles, aren't they stronger because you never get really white in here? But okay, I believe, fine. My question was a different one. When you were talking about the line widths, you said there's evidence from carbon 1. Or was it C2? I don't remember.
No, it's oxygen 1. I mean, there is the intersystem line from oxygen at 1356 angstrom. It's very interesting. It's unfortunately very, very weak. So you need extremely long exposures with iris, but it is optically thin because it's formed by recombination.
Right.
And it's formed in the chromosphere. So it is a really good indicator of what you can allow in non-thermal motions. And it is in the darkest areas in iris. Of course, there it's extremely difficult to make the observation, but it seems that it is no wider than the instrument width of iris. So you cannot have more than 3 kilometers per second or so of microturbulence.
Right. That's interesting. Is this published?
It's sort of. I mean, it's mentioned in the annual review of astronomy and astrophysics, the new chromosphere paper.
Right. Okay.
But we're working on a specific paper on that result as well.
Mm-hmm. Right. Okay. Thanks.
There's a question in the chat box by Nat Gopal Swami. Do you want to unmute and ask by yourself? Okay, I can read it out in that case.
Well, I can have a check. I had to switch off the.
Okay, can you hear me now?
Yes.
Yes.
Okay, Mats, my question is, you said that higher magnetic field suppresses the activities in the chromosphere. We also know that when you have higher magnetic field in the photospheric level, the resulting solar wind has higher speed.
Yeah.
So which basically means that you have some kind of more activity in terms of waves or whatever is heating the atmosphere and letting the plasma go out.
Yeah, I think that, well, we see also more of sound waves propagating along the field in these open field regions in the simulation. But what I said with suppression of chromospheric variability is more these big, large-scale vortices or throwing up of chromospheric material to 10 megameters. It's that part that I meant.
Okay.
But certainly you can have easily imagine that you have a more of an acceleration of a solar wind in these regions.
So
more waves.
Those two types of activities in some way influencing each other because you have the lifting suppressed, you have more waves. Some kind of energy partition changes.
Yeah, I mean, the field certainly will suppress horizontal motions.
Okay.
Except, I mean, you do have horizontal motions in the form of transverse waves propagating along the field. But to have a large-scale horizontal distribution of or redistribution of mass across the field is prohibited.
Interesting. Thank you.
Probably we can take one short question. Tanmay, can you go ahead?
Hi, Matt. I have a basic question. So what is the main source of the heating in this simulation? Like, is it due to ohmic dissipation or reconnection? And also we know that the shock heating plays an important role in heating of the chromosphere. So are this simulation include shock heating?
I mean, the simulations are dominated by the ohmic dissipation when it comes to converting magnetic energy to thermal energy. And it is with a hyperdiffusion scheme that is rather similar to the anomalous resistivity scheme of Yokoyama and Shibata. So it does allow reconnection, but it's not sort of reconnection in the scales where it will happen in reality. So it is that you do convert, you do store energy from the foot point motions, and it's dissipated, but the exact dissipation mechanism is different than in the sun. And probably also the reconnection in the sun will be more non-local, that you will accelerate electrons that will deposit the energy in a very different place. And that is also something we're looking into. But also shock heating is present and it's important. So, but again, of course, the shocks are much more distributed because of the limited numerical resolution than you would expect in reality.
Okay, since this is the last session, probably we can take one more question by Arnav. Do you want to go ahead?
Okay, sure. My question is related to the local dynamo which you find in your simulation of the quiet region. So my question is, do you find an equipartition of magnetic energy with fluid kinetic energy? And how do the scales of magnetic field compare with the scales of velocities field? And I suppose in imaged simulations, often these things depend on the magnetic Prandtl number. So did you, what sort of magnetic Prandtl number did you use? And did you ever study the effect of varying magnetic Prandtl number?
I mean, it is a bit difficult since we have these, diffusivities and viscosities are dependent on, they are not the physical ones, they are numerical. So they we dissipate the energy when it's needed for numerical stability, basically. Okay. So it's difficult to define Prandtl numbers or Reynolds numbers. But we haven't looked into, have started to look into these questions. It seems that from a very a basic comparison that we get pretty much the same result as Matthias Rempel in his Muram simulations. But we haven't looked at, and we have started to compare by setting more fixed viscosities and varying the parameters to really look into these questions, but we haven't done that yet.
Okay.
I think Vishal also has a question. Maybe we can take that also. It won't exceed much time. Yeah, Vishal, you can go ahead.
Thanks, Nitin. Hi, Max. This is Vishal here from Ayuka. It was a very nice talk. So I had two questions. First is, as you mentioned, the generation of a small-scale dynamo in the Quaitson simulation. So is this something observable? And if so, what are the signatures for this thing? The second question, okay, you can answer this question first, then I'll go to the second question.
Yeah, I mean, we see that a lot of the magnetic field is not dependent on the solar cycle. And that has been interpreted as a sign that there is something rather than a global dynamo in operation.
Mm-hmm. So is that something like probing the Doppler velocities, Doppler shifts or something can be figured out for a given field of view if there's a dynamo action going on? Is it possible, or are these too small to be resolved by our instruments?
I think that, I mean, you do look at the distributions of a magnetic field and the correlations in order to address these scales. I mean, you could explain part of the small scale field could be due to the larger scale field that is just, decaying active regions and so on, but you would then expect to have a correlation with the cycle. And some of these things are not correlated with the cycle. And also, I think that it's rather inevitable when you have the type of convection that you have in the sun, that you also do generate the field.
I see. So second question is, so in the coronal hole simulation, you mentioned that on increasing the field strength to pi Gauss, the activity was suppressed. But did you look at these small scale velocities and did you find some relation that the velocities have gone down or something like that?
We haven't looked at that, and I saw your poster.
Yeah.
Yes, that's something that we would like to look into.
Yes, I have some velocity measurements there. So, but you had commented on the intensities alone. So you can have a look at that. That's what I'm trying to figure the poster out, essentially. Yeah. Thank you very much. Thank you, Nitin, for letting me ask.
You're welcome. Yeah, thanks a lot for the nice discussion here. So yeah, thanks again, Matt. So now we move to the next speaker. So next talk is by Anusha, and she will be talking about non-equilibrium equation of state for the solar atmosphere. So over to you, Anusha. Now you can share your slides and begin.
Can you see my screen?
Yes.
Okay. Yeah. Thank you, organizers, for providing me an opportunity to present my work in this 50th anniversary of IAA. It's nice to be part of the conference. So I start by saying that we are interested in the solar chromosphere. Thanks, Max, already for setting the stage. I won't go into the details. We are interested in the low density chromosphere, and in particular, we are interested in understanding the role of radiation field in chromospheric heating. Now that there are new observations of the chromosphere in calcium 2H and magnesium H and K passbands are expected from Soot on board Aditya, and there is a NLST project coming up, and also new observations from DKIST are already starting to come up, and ever-increasing computer power allows us to address the numerically challenging simulations of the chromosphere. Now, I start with the radiative transfer equation. This is a general form of the transfer equation, where I is the specific intensity, S is the source function, which is the ratio of emissivity to absorptivity, and X is the frequency, R is the position vector, omega is the ray direction. Now, this is the formal solution of the radiative transfer equation, which has two parts. This is the directly transmitted part and this is the local part. As the emissivity and absorptivity both depend on N, which is the population of the constituent of the gas, and which in turn depends on intensity through the rate matrix, which I come to that later. The intensity now depends on intensity itself within the integral, which makes it an integral differential equation, which makes it highly nonlinear and complex to solve. And an important quantity that drives the non-LT effects, which I come to that later as well, is the mean intensity term, which is the integral of the intensity over all frequencies and directions, with phi here being the fourth profile function representing the complete frequency redistribution. Now, the approximation of local thermodynamic equilibrium is not, it's valid when the scattering of radiation is insignificant, for example, for the photosphere, where radiative transfer solution is trivial. But it cannot be assumed in the chromosphere, where scattering becomes important. And here, the radiative transfer equation is non-trivial, non-linear, and it's called as the non-LTE radiative transfer equation. LTE has a limited applicability, and in general, to compute the actual occupation numbers of the bound and free states in static stellar atmospheres, one uses the non-LTE kinetic equilibrium or statistical equilibrium equation. And again, as I mentioned before, the driving term here is the mean intensity term J bar, which brings the non-LTE effects through all these processes. This is the form of the non-LTE rate equation or the kinetic equilibrium equation, where CLL prime is the collision rate, R represents the radiative rate, NL and NL prime are the populations. Now, the collisional and radiative processes here are balancing with each other to have a zero right-hand side. On the other hand, Klein and Knier already demonstrated that this statistical equilibrium is also invalid in dynamic atmosphere with shock waves. From 1D simulations, Carlson and Stein found that the chromosphere hydrogen ionization recombination time scales within hot shocks is 50 seconds, whereas within cool intershock regions, it can be as high as 10 power 3 to 10 power 5 seconds. Therefore, the time scales on which the atomic populations reach equilibrium with their environment is much more than the evolution time scales of the environment itself. And therefore, equilibrium is never reached. This is where we have to solve the non-equilibrium ionization problem, which is even more general, time-dependent, and non-linear radiative transfer problem. This is the form of the rate system for the non-equilibrium case, where the left-hand side looks similar to the kinetic equilibrium equation with collisional and radiative rates, but now we do not have a zero right-hand side, but it depends on the right-hand side is now contains the d and dt, which is the change in populations and an attraction term. There have been several attempts to model solar chromosphere. On the one hand, we have this Radin code of Carlson and Stein, which solves 1D hydrodynamical equations together with non-equilibrium and non-LTE radiative transfer using adaptive mesh algorithm. However, Radin is a hydrodynamical code, and since it's a 1D hydrodynamical code, magnetic fields cannot be taken into account, and also this is not suitable for 3D MHD simulations as it uses the adaptive mesh algorithm. On the other hand, the Bifrost code can do radiative MHD simulations in multi-dimensions, but which also takes into account the non-equilibrium effects. However, there are several approximations in missing physics in their formulation, such as time dependence is neglected in the rate system, and equation of state and radiative transfer calculations are approximated by using prescribed recipes for chromospheric radiative losses. Therefore, in this project, we focus on developing a new numerical method to solve the non-LTE non-equilibrium radiative transfer problem through a proper time-dependent treatment of radiation field and the rate system, a proper non-equilibrium treatment of the molecular chemistry for the equation of state, and development of a time-implicit numerical scheme that can take larger time step, and which is also suitable for 1D, 2D, and 3D. With these steps, we have developed a radiative transfer module for MURAM, and the method is presented in this paper. In this talk, I will focus on the numerical method itself. So this has two steps. The first step is the formal solution of the radiative transfer equation, and the second step is to solve the rate system. So our method is a generalization to time of the short characteristic formal solution of the Konashen and Auer-Pellet papers, and also generalization of the preconditioned multi-level approximate lambda iteration scheme of Rybicki-Hammar to solve the rate system. To recall, this is the form of the non-equilibrium rate system, integrating which we have a population evolution equation given here. Here, n of t is the population at time t, which depends on population at time tn, and integrating which on tn to t, this is the integral of the rate system, and this is the advection part. Now, to find a solution to this system, we follow the ideas that led to the short characteristic form solution method originally developed for the non-LTE radiative transfer equation in the multidimensional geometry. We apply the same ideas, but now in time. So for that, first we define time step as follows. We are interested in evaluating n of t at delta t for each time step. The main idea here is that all the time-dependent quantities are expressed as linear polynomials in t that use the known values of this quantity at previous time step. This is exactly the idea used in the short characteristic method, where the source function was expressed in terms of polynomials in spatial variable that uses the known values of source function at 3 or 2 grid points. And here, further, we ignore all the cross terms of second and higher order. This leads to the linear polynomial form of the population, temperature, electron density, collision rate, etc. And by substituting all these, it allows a direct evaluation of the time integration of the rate system and evolution equation, and it yields a linear system of equations. This is the form of the source function now, which is similar to the short characteristic source function, but now it also depends on time. And this is the form of the intensity. Now the second step is to solve the rate system. So to recall, this is the form of the rate system. Now to recall, the radiative rate here contains the term mean intensity term, which is important and drives the non-LTE effects. Therefore, here instead of radiative rate, I just write J bar term here. To compare with the kinetic equilibrium equation, in original kinetic equilibrium form, the rate system A depends on the collisional and radiative rates, and we are solving for a population with 0 right-hand side. For the non-equilibrium case, we construct moments of collisional and radiative rates as follows. And now we are solving the rate system. That rate system depends on the second moment of the collisional and radiative rates on the left-hand side. Whereas we don't have a 0 right-hand side, but now the right-hand side vector depends on the first moments of the collisional and the radiative rate. And we are solving for the population derivatives. So this makes it even more nonlinear and complex. And the rate system now looks like this, and we look for solution of this form. And similar to the original Rybicki-Hammer method, we also have terms of the form NL dot and NM dot, which are products of the solutions of the population derivatives, to linearize which we have to use one of them to be from the previous iteration. Now, with all this, finally, we verified that our method is correct by comparing with the well-established benchmark solutions. The first benchmark solution that we compare is that when non-equilibrium system left to itself reaches the equilibrium, which is the kinetic equilibrium solution. And from RH code of Eitenbrook, we can get independent kinetic equilibrium solutions, and we can compare these two. And similarly, we also computed the time scales of the ionization and recombination and compared those with the time scales computed by Carlson and Stein in 2002. Here, we recall that the time required for a system to change by a value of E is called as the physical time scale. Now, the first verification here, here we have electron density, which is fixed, and ground state, first excited and ionized state of hydrogen, and the dashed as a function of height. The dashed line here is the solution from RH code of Eitenbrook, and all the colored lines are starting from LTE solution, our non-equilibrium solutions at different times, which are shown in this color bar. And you can see that our non-equilibrium solution nicely reaches the equilibrium solution, which is similar to, which matches very well with the kinetic equilibrium solution from the RH code. In the second case, we plot here temperature in kilokelvin as a function of column mass for different temperature structures taken from publicly available Bifrost simulation. And for each of the temperature structure, we compute the time scales following the method described in Carlson and Stein. And we plot the logarithm of time scale here as a function of column mass, and you can see that it varies more than 2.5 orders of magnitude from time scales of minutes to hours. And this particular time scale with dashed line compares very well with the values obtained by Carlson and Sten. To summarize, we have developed a new numerical method, and it is developed for 1D, 2D, 3D, currently tested in 1D in this paper. And it is a generalization of these two methods, and it has been verified by comparing with the benchmark solutions. These are presented in this paper. And of course, the next step is to iteratively and self-consistently solve the MHD and radiative transfer modules for the dynamic case to simulate the dynamic solar atmosphere. And two important quantities that we contribute from the radiative transfer module to the MHD are the pressure for the momentum equation and flux divergence for the energy equation. Thank you.
Thank you, Anusha, for a very nice talk. The floor is now open for questions or any comments. I do not see any questions or comments for now, but if you have any questions.
I think Ronnie Gibbons has a question. He has raised his hand.
Okay, sorry, I cannot see it.
Right. Yes, thanks for the talk. I was wondering, is this going to be open source, and is it going to be suited for also block hierarchical AMR meshes?
Right now, no, because it's still in the development stage. I'm testing the dynamical part. So soon it won't be public, sorry.
Okay, thanks.
Mats, you can go ahead.
Yeah, thank you very much for a nice talk and very nice work. Do you have any idea of how long it will take, or, I mean, running Muram with or without this module? What would be the
Yes, I was expecting this question. There are two main problems. I mean, the main reasons for the slowness of the code. That is, one is the explicit wavelength dependence of the radiative and related quantities. We take explicit wavelength dependence. And the second is that the intensity that I showed here, to evaluate this, we have to use exponential integrals in certain cases. And there are many cases where, depending on the value of tau, we have to evaluate indifferently. But main problem is, in a major part, we have to evaluate with using exponential integral. Because of these two reasons, the code is much slower compared to the LTE Muram version. And at the moment, for a typical of 2.8 megameters with 150 points and 100 wavelength points, and with at that time step of milliseconds, it can take 1 to 1.5 minutes per time step, which also includes Lyman alpha, that is the 3-level hydrogen case, and also at this time step, it takes around 20 to 30 iterations per time step.
Okay, thank you.
Any more questions?
Yeah, Oscar has also raised his hand.
Yes, maybe just to this slide, as you say, this evaluation of the exponential costs time, but you should not, they should be expanded, these exponentials. And
yes,
then,
but the thing is, when the actual module that we use for the exponential integral uses long double, and then there are situations like the product of two terms, we get a product of two terms for evaluating this. And if I don't use long double, it can cause infinity, because there are products in such a way that it causes numerical problems. So I have to use long double as to precisely evaluate this rate system and several parts. That also causes the time delay, actually.
okay, good. Thank you.
Thanks for the question. So yeah, over to you, Supriya.
Yeah, thank you, Anusha, again. We can move on to the next speaker, Sampurna, who will talk about probing the vector magnetic fields from resonance line polarization. Sampurna, you can share your screen.
Yeah. Okay. So good evening. Today I will be presenting our work connected to probing the vector magnetic fields from resonance line polarization. Scattering of the solar limb darkened radiation field by atoms and molecules produces the linearly polarized spectrum of the sun, the so-called second solar spectrum. There are several strong resonance lines in this spectrum that can be explained only when partial frequency redistribution, PRD in line scattering, is accounted for. For example, below I show the polarimetric observations of two strong resonance lines, the sodium 1D2 to the left and calcium 14227 to the right, taken with Zimpone. The bottom panel, which shows the Q by I, we see that both the lines exhibit a typical triple peak structure, which is due to PRD. This non-magnetic resonance line polarization is modified in the presence of a weak magnetic field via the Hanle effect. Hanle effect occurs when the magnetic splitting, which is given by G omega L, G is the Landé factor and omega L is the Larmor frequency, is comparable to the radiative width of the upper level. Hanle effect causes a modification to the non-magnetic Q by I, and also it rotates the plane of polarization. Hanle effect can detect both directed and turbulent fields and has been used to detect weak fields on the sun. Now, if the fields are stronger, such that the magnetic splitting is much larger than the radiative width, but comparable to the Doppler width, all of us know we have Zeeman effect, and this audience needs no description of it. And it has been used for more than a century to detect magnetic fields on the sun. Now, coming to the Paschen-Bach effect, here I will discuss this effect in the context of a two-level atom with HFS. When an atom possesses a non-zero nuclear spin, the fine structure states of the atom undergo hyperfine structure splitting. So we have F states, and in the presence of magnetic field, the F states further split into magnetic substates. Now, depending on the field strength, we have different regimes. Now, if the magnetic splitting is much less than the HFS, we are in the linear Hanle-Zeeman regime, wherein the magnetic splitting varies linearly with the field strength. If the magnetic splitting is comparable to the HFS, we are in the incomplete Paschen-Bach effect regime, and this regime is characterized by nonlinear splitting of the magnetic substates, the level crossing, and anti-level crossing effects. Then if the magnetic splitting is much larger than the HFS, we enter the complete PBE regime, wherein the magnetic splitting again varies linearly with the field strength. So there are several resonance lines in the second solar spectrum that sensitively is affected by these magnetic field effects, and therefore offer a diagnostic potential to detect solar vector magnetic fields. To exploit this, it is first essential to solve the polarized transfer equation, including the effects of PRD and arbitrary strength magnetic fields. The polarized transfer equation for the Stokes vectors IQUV is given here. For a planar atmosphere, K is the total absorption matrix, and it is a sum of the line absorption matrix plus the continuum, which absorbs isotropically. The line absorption matrix has this well-known form, where phi's are the absorption coefficients, which are different for different polarization states, and chi's are the anomalous dispersion coefficients, which basically describe the magneto-optical effects, namely the Faraday rotation and the Fort effect. The total source vector is the sum of the polarized thermal emission plus the scattering contribution, and the scattering integral is given by the product of the redistribution matrix times the incoming intensity integrated over all angles and frequencies. the PRD matrix depends on the atomic system chosen. For example, for a two-level atom without HFS, this matrix has been derived in Beaumier 1997 using a quantum electrodynamic approach. For a two-level atom with HFS, this matrix is derived in the absence of elastic collisions in Soumya et al. 2014 using a Kramers-Heisenberg scattering approach of Stenflo, and more recently in Beaumier 2017, where even the collisions are taken into account. One of the first attempts to solve this complex transfer equation for a two-level atomic system without HFS was by ourselves, where we used a simple perturbation method. More recently, an accelerated lambda iteration method to solve the same problem has been presented in Alcina Ballester et al. 2017 and also in our work. We have applied this Ali-based method to the case of two-level atom with HFS in these references. Now I will describe very briefly the numerical method of solution. The formal solution of the transfer equation can be written in terms of the lambda operator, which is now both frequency and angle dependent. And following Cannon, we introduced the operator splitting in this way, where lambda star is the approximate operator, and following Olsen et al., it is taken to be diagonal. With this, we can set up an iterative scheme in this way to compute the source vector at each iterate. And the source vector corrections is given by this expression. So here on the right-hand side, Fs means the formal solution, the source vector obtained by obtaining formal solution of the previous iterative source vector. And for the formal solution, we use the Delopar method of Trujillo-Buono 2003. This is a linear system of equation which can be written in this matrix form. And this is a huge system because we have to take large frequency bandwidths, and also the radiation field inclination and azimuth needs to be taken into account. To reduce the computational cost, we apply the Ali technique only to the intensity component, namely SI, because it drives the convergence rate. And other polarization components of the source vector are computed using the so-called scattering expansion method, which is described in Frisch et al. And I will not go into the details. So for our numerical studies, we consider an atomic system representative of the D2 line of sodium-1. The D2 line results from a Ju equal to 3/2 to Jl equal to 1/2 transition, and all the atomic parameters and the HFS constants are given in this table. Because the computations are expensive, for exploratory purposes, we have used isothermal planar model atmospheres, which are characterized by this set of parameters. We have chosen an atmosphere which is nearly semi-infinite. The field geometry is chosen to be horizontal, and the line of sight is chosen as nearly tangent to the limb. In the incomplete Fashionback effect regime, the magnetic splitting is not given by G omega L, but rather has to be determined by diagonalizing the magnetic Hamiltonian. And the resulting eigenenergy values for a range of field strengths between 0 to 300 Gauss are shown in this level crossing diagrams. The left panel is for the lower level of the sodium D2 line, and the middle panel is for the upper level. In the field strength range considered, we do not see any level crossing in the lower level, but in the upper level, we see about 14 level crossings as shown in this zoomed in panel to the rightmost. As the field, so this field strength regime is between 0 and 50 Gauss. As the field strength goes beyond 50 Gauss, the magnetic substates start to bunch together, indicating that there is a gradual transition from the incomplete to the complete PBE regime. So here we show the effect of field strength variation on emergent Stokes profiles. So what is plotted is Stokes I, Q by I, U by I, and V by I versus delta lambda. And in the leftmost panel, we vary the field strength from 0 to 10 Gauss, in the middle from 10 to 30, and in the rightmost from 50 to 300 Gauss. And in all the panels, the non-magnetic reference case is shown as the black solid line. So one can note the typical signatures of PRD. In intensity, we obtain a deep absorption line with broad damping wings. And in Q by I, we have a line core peak and two wing PRD peaks, one in the near wing and one in the far wing, due to the choice of the model atmosphere. Intensity is insensitive to increase in B because the HFS magnetic splittings that we have is much less than the Doppler width that we have chosen. In the V by I profiles, we see that they are asymmetric in the incomplete PBE regime. So for fields less than 30 Gauss. And this is because of the nonlinear splitting of the magnetic components in the incomplete PBE regime.
Sampurna, you have 2 more minutes.
Okay, sure. And for fields larger than 30 Gauss, we see that V by I profiles start to become more and more antisymmetric. So thus a non-zero net circular polarization seen in the incomplete PBE regime, as noted also in Lopez Arista et al. 2000. Now coming to the linear polarization. So the linear polarization shown here is zoomed in here to show details in the line core and the near wings. So in the leftmost panel, we can see that when the field strength changes from 0 to 10 Gauss, the field Q by I decreases and the U by I is generated. That is typical Hanley effect. And in the middle panel, where we go from 10 Gauss to 50 Gauss, we can see the level crossing effects, namely the Q by I no longer decreases, but it starts to move towards the non-magnetic case, and the U by I starts to move towards the, again, the non-magnetic case. This is due to the level crossing effects. In the wings, the Hanley effect is known to operate mainly in the line core, but we see that the wings are highly sensitive to the magnetic field strength, and this has been shown by Alcina Ballester et al. 2017 to be due to the magneto-optical effects. In particular, the Faraday rotation, that is the chi-V turn in the absorption matrix, basically couples Q and U, and therefore converts the Q by I in the wings to U by I. And for fields larger than 50 Gauss, that is the rightmost column, the wings are highly suppressed, and we see Z1-like signatures in the line core. So coming to the conclusions, resonance line polarization provides a sensitive diagnostic tool to probe the solar vector magnetic fields. So we have solved here a polarized line transfer equation, including PRD and arbitrary strength magnetic fields. For computational simplicity, we consider isothermal atmospheres, and the numerical solutions are presented for atomic systems representative of the D2 line of sodium-1 and for field strengths in the range 0 to 300 Gauss. We have shown the signatures of level crossing, nonlinear and asymmetric splitting, magneto-optical effects, and PRD, apart from those due to Hanley and Zeeman effects. And further work, we are now looking at including the realistic solar model atmospheres in this problem. So thank you for your attention. And I also thank the organizers for the opportunity to present this work here. Thank you.
Thank you, Sampurna, for nice talk. And yeah, so session is open for the questions. You may raise your hand if you have any question or comment. Yeah, I don't see any questions. So thanks again, Sampurna. Yeah, so over to you, Supriya.
Yeah. The next talk is by Peter Young on coronal models. A recorded version of his talk will be played now, and Peter will try and join us by the end of the question and answer sessions to answer if there are any questions. Probably if you have more questions, you can also type in the chat window so that if as soon as he is online, he can have a look at it.
everyone. My name is Peter Young, and I work at NASA Goddard Space Flight Center. I'd like to thank the organizers for giving me a chance to speak today. Since it's early in the morning in Washington, D.C., I thought it best to record my presentation in advance, but I'll join for the questions afterwards. My topic is coronal spectroscopy and modeling, and I'll have a particular focus on how mission teams can make the process of analyzing spectral data easier. Given that India is about to launch its first solar mission, then this information may be useful as your instrument teams prepare for the post-launch operations phase. For the first part of my talk, I'll cover some basic facts about the spectrum from the corona. The spectrum is produced following collisions of ions with electrons at about 1 million degrees. The thermal energy of the electrons converts to a wavelength of around about 150 angstroms, and so we expect the emission lines to be found at extreme ultraviolet and soft X-ray wavelengths. Iron is the most important coronal element, as other abundant elements are either fully ionized in the corona, so hydrogen and helium, or they have simple atomic forms that produce few lines. Iron is the only one which retains complex atomic structure at coronal temperatures, and this leads to a larger number of emission lines and thus a large number of plasma diagnostics. So here in the bottom of this slide, I show a low-resolution ion spectrum, and the key ions, wavelengths, and transitions are indicated. The iron 9 to iron 14 group, around 170 to 220 angstroms, is the most famous, and you're probably familiar with the AIA 171, 193, and 211 channels that pick out emission lines in this region. The iron 15 and iron 16 lines have also been well studied in the past, but the two groups of hotter ions at shorter X-ray wavelengths have been much less studied, although the sounding rockets Magix and Eunice will hopefully observe some of them later this year. The emission lines in the previous slide are all what we call allowed atomic transitions, which means they have high rates of occurrence. In this slide, I'm showing a simple atomic level diagram for one of these ions, iron 18. And there are two allowed transitions originating from the upper atomic level shown here, with an energy difference around about 100 electron volts. One option is to decay to the ground atomic level, but there's also a low-lying level nearby to which the ion can also decay. This low-lying level gives rise to a so-called forbidden transition. It's not actually forbidden, but has a very low occurrence rate. Despite this low rate of occurrence, the resulting emission line is actually quite strong. And so what I'm showing here is a synthetic spectrum showing just the iron 18 lines between 50 and 1,000 angstroms. So the two allowed transitions in the plot above appear close to 100 angstroms, but the forbidden line, because of the much smaller energy difference, appears at a much longer wavelength, closer to 1,000 angstroms. But as you see in the spectrum, forbidden line, when shown in photon units, is actually stronger than the two allowed lines. This means it's a very nice way of accessing the iron 18 plasma at longer wavelengths. Now, this plot, what I've done here is take all of the coronal ions and plotted their strongest forbidden lines as a function of wavelength. So all of the lines are above 500 angstroms. Many of the cooler ion lines are in the visible and near infrared, giving access to the corona from the ground, although only above the limb. And of course, these lines have been observed for decades during eclipses and more recently with ground-based coronagraphs. VEL-C on Aditya will observe 3 of these lines, and I've indicated those in blue here. The lines in the far ultraviolet around 500 to 1,500 angstroms are also convenient, as they can be observed simultaneously with cooler lines from the chromosphere and transition region. Examples include the iron 21 1354 angstrom line observed by IRIS, and also there's 2 lines observed by SPICE and Solar Orbit. These lines are indicated on the plot in different colors. Okay, so the second part of my talk, I'll say a little bit about Chianti. This is an atomic database and software package for modeling the emission from optically thin plasmas. It's been freely available for almost 25 years now, and it's maintained by Ken Deere, Giulio Dalzana, Enrico Landi, and myself. I consider it to be critical infrastructure for solar physics. It's not only used for spectroscopy, but also for predicting line emission from 3D plasma codes and for helping instrument teams with count rate predictions, for example, or calibration work. Version 10 of Chianti was released just last year, and the paper is in press. Okay, I'll briefly describe two new features of Chianti that came out with version 10. Since the beginning, the Chianti software has always computed emission line emissivities directly from the atomic data as they're requested from the user. Computing a synthetic spectrum can take a long time, and this has only got worse with time as we've introduced larger and larger atomic models. To help get around this, we now have level population lookup tables that greatly increase the calculation speed. This can be very useful for DEM analysis, for example, or computing line intensities from plasma simulations. We've added a number of new routines and made modifications to existing ones. In the bottom right, you'll see a screenshot from the ch_ss routine, which is used for computing synthetic spectra. And you'll see there's now a lookup table option, which you're able to use now. For more details about this, please check out our Chianti technical report number 16, which is available on our website. Okay, the next feature is what we call DR suppression. So we distribute with Chianti a table of ionization equilibrium curves, showing how the populations of the ions change with temperature. There is no density dependence, yet we know that the atomic process dielectronic recombination, or DR, becomes suppressed at high density, which affects the equilibrium curves. We've added formulae for modeling the suppression of DR that were published by Nikolic et al. In 2018. So new software computes INEQ tables for specified densities or pressures that can then be input to the Chianti software in the usual way. In the bottom left here, I'm showing the results for the ion oxygen 6. The white curve is the original so-called zero density curve, which is the default in Chianti. And the other curves are computed at 3 different densities. You see there's quite a big effect in terms of the increasing the ion population of oxygen 6. Again, we have a Chianti technical report on this new feature, and it's number 17, which is available on the website. Okay, so the next part of my talk deals with my experience of developing software tools and documentation for the ICE instrument on Hinode. As I thought this might be of interest for the Aditya instrument teams as they get ready for the operations phase of the mission. So Hinode was launched in 2006, and ICE is one of 3 instruments. It's an EUV imaging spectrometer that mainly focuses on coronal emission lines. Now, in a world where EUV images and line-of-sight magnetograms are readily available to the community, it can be difficult to persuade young scientists to use spectral data due to the extra processing steps required to get scientific results out. It is therefore crucial, in my opinion, for the mission team to provide analysis software and documentation to make it easy for users to get started with the data and derive results that show the power of the instrument. So a large chunk of the time I've spent on the ICE project has been on these efforts, and I'll describe some of them here. Okay, so firstly, I thought I'd give some advice on how instrument team members should approach this challenge. And I came up with these 5 points written here. So all space data are affected to some extent by instrumental effects that get in the way of the data analysis. So it's important for the team to identify these effects and make sure they describe them in documentation. They should also provide fixes to these instrumental effects, either by producing a corrected data file, often referred to as a level 2 data file, or by providing software fixes. In the case of our ICE, we chose the software fix route, whereas IRIS, for example, it chose the route of creating the level 2 files, which they distribute to users. Also, since the instrument team will have scientists who will be analyzing the data, then I think it's important that these team members make their analysis software available. It also, as well as being directly useful for users, it also gives confidence to the users knowing that the team is using exactly the same software that they are. I also think tutorials are very important for allowing new users to get started with the data. Crucially, the tutorials should be more than just how to download data and plot an image. They should show how to obtain useful scientific products from the instrument. Finally, you should avoid what I call the secret software syndrome, whereby team members have nifty software that they keep for themselves. You might hear people saying things like, oh, well, it's very complicated and difficult to explain. So it's not really worth my while to make my software available. Or they may say, well, if I make my software publicly available, people are going to find bugs. And I'm going to be spending all my time trying to fix these bugs. In my experience, getting your software into a state that other people can use it easily makes the software better, and I believe is well worth the effort. And also on this point, one suggestion I have for other instrument teams is that it would be a good idea to create a role of what I may call a data analysis coordinator, someone to oversee the software and documentation and make sure it gets out to the community. We didn't actually have this for ICE, but I kind of ended up taking it on myself in an informal way as the project went on. Okay, so we start with the documentation. Then there was two approaches that the ICE team took. Initially, we started off with the ICE wiki. So wiki is a web page that any of the team members are able to log into and edit. And I thought this was a very good way of quickly getting information out to the community early in the mission. Fortunately, it didn't really have much structure. People kind of just edited things into the web page as they went along. And so after a while, there was so much information there that it wasn't really easy for a new user to follow it. So in the end, I decided to take the decision to reorganize the page, giving it some structure, and basically creating something more like a standard data analysis guide. And that's what I'm showing on the slide here in the screenshot. And so still all the original information is there. I'm giving links to it, so it makes it more easy for the new user to read it. Amongst other things, this wiki page, it includes the tutorials, which I recommended on the previous slide, taking you through the steps of how to analyze the data. I still think the wiki is a very good way to go for an instrument team due to the ease of being able to edit the pages. But I think having your coordinator, your data analysis coordinator, to oversee it is a recommended way to go. Okay, the second part of the ICE documentation is a set of software notes, each of which is a document describing a specific aspect of the mission. For example, instrumental effects, software, or data format. The idea is that the software note contains the best available information about these specific issues. The advantage over a single large analysis guide is that different individuals can have responsibility for these notes, giving less burden on a single person who's maintaining the entire analysis guide. Okay, in terms of, I mentioned instrumental effects before, and so one particularly annoying one for ICE has been warm pixels that arise because our CCDs are running hotter than expected. They currently make up about 25% of the CCD pixels. And you can see their effect on the raster image on the left at the bottom of the slide. Each one pixel gives a horizontal line as ICE does the raster. And you can see it makes a bit of a mess of the image there. So I developed software to replace the one pixels through an imputation process. And I also wrote software to deal with the weakest one pixel values, as these can be a real pain when you get to low signal areas, as I'll show later on at the end of the talk. So this work is described in our ICE software notes number 6, 13, and 24. Okay, so now moving on to analysis software that I've written for ICE. The first I want to highlight is something called ICE Mapper. Ostensibly, it's quite simple. There's a web page given here at the bottom of the page. And for each day of the mission, it's been 14 years now, you'll find an image of the sun with locations observed by ice indicated by boxes, as you see in the image on the slide here. Because ice has a relatively small field of view, then such a site is surprisingly useful for quickly working out what ice was doing on any given day. In addition to providing you the web page, I also made the software that generates the pages publicly available. And so it's easy to generate the pages for yourself. You can also do customization to perhaps show only specific data sets, for example. Okay, another routine I wrote is ICE raster browser. And the widget display is shown in the slide here. So an imaging spectrometer produces 3D data sets of X, Y, spatial information, and wavelength. And so this tool allows you to quickly browse the 3D data cubes. So this is illustrated here for an active region raster. There's 4 columns here showing 4 different emission lines in the ice spectrum. The top row gives images in these emission lines, and you'll see the crosses on the images. They indicate a specific spatial pixel, and the spectrum of that pixel is shown on the bottom row of plots here. So I find this software so useful for quickly browsing the data that when I gained access to the IRIS data back in 2013, one of the first things I did was to take my raster browser software and make a version for IRIS raster browser. And the Oslo group have also developed a version of raster browser for the SPICE instrument as well. That's based on my code. Okay, now for any UV spectroscopy mission, Gaussian fitting of emission lines is a basic requirement. There are 2 cases. The first is when you want to average an average spectrum for a specific spatial structure, as illustrated in the bottom left image, showing a bright point. And hopefully you can see little crosses where I've picked out the brightest parts of the bright point. So you graphically choose a mask corresponding to the feature. The software then goes and averages the spectra over this spatial region. And then I have a separate routine called SpecGauss ICE, which then takes that single spectrum and allows you to go through and manually fit the emission lines that you're interested in. And that's what you're seeing on the right-hand side there. And so the other type of Gaussian fitting we have is when you want to take a raster image with many, it might be 100 pixels by 100 pixels, and automatically fit Gaussians at every single spatial pixel in that image. And that's what I call autofit. I've written down the process of how the autofit routines work. Firstly, you create a fit template telling the software which specific emission lines you want to fit. There's another routine which then allows you to choose the exact wavelength region that you want to fit. You then perform the fit with ICE autofit, and then we'll have a graphic-based routine called ICE Fit Viewer that then allows you to browse the quality of the fits. That's what you see here. The top row of images on the left-hand side shows the intensity image. The next column shows the velocity Doppler image. You see in particular here, there's a very nice active region outflow region, which you see is this sort of blue fountain at the top left. The next column shows the emission line width, and the 4th column shows the chi-squared for the fits. And the bottom row, bottom left, shows an example fit for one of the pixels. Anyway, and if you're happy with the fit after having a view of it, then you can extract the fit parameters and do your science with those parameters. So all of this is described along with examples in my software notes 16 and 17 and in the online tutorial. Okay, when taking that fitting software and then interfacing with Chianti, you can then derive some plasma diagnostics. And so, for example, here we have a density-sensitive line ratio of iron 14. After fitting the 2 lines with AutoFit, I have software that then interfaces with Chianti to yield an electron density map of the active region. Thus, the user can go from the ICE data file to a density map with just a few minutes of work. Okay, the final part of my talk, I'll briefly describe my role in a project for connecting the corona to the solar wind. The project's based at NASA Goddard and is led by Nikki Vial. The aim is to trace plasma from the corona through the solar wind and up to the Earth's magnetosphere. Particular focus is on understanding periodic density structures seen in the solar wind. Examples are in the figure here on the slide. And these are likely related to reconnection occurring in the corona. My particular role in the project is to analyze ice data as element abundance ratios and plasma temperature are measurements that potentially can lead us to identify solar wind source regions. So to show how my research work interfaces with my community work, I'll list here the activities I've been performing on the project. I mentioned earlier my ice mapper software, which was specifically developed for this project so that the other team members would have an easy way of seeing where ice was pointed on any given day. This allowed us to find the best days when we felt we could make connections to the solar wind. I also mentioned earlier the warm pixels in the ice data. We know the solar wind is associated with the coronal holes, but coronal holes have low signal in ice data. A consequence is that the weak warm pixels add an extra component of noise in these regions that impact emission line measurements. I thus came up with a new technique for flagging and removing these pixels, as I described earlier. I've also worked on scattered light and new DM software that I'll describe in the next 2 slides. So our project requires studies of on-disk coronal holes, since we're looking for connections to the solar wind. We know scattered light is a problem for coronal lines, and so I used data from the Venus transit in 2012 to derive an empirical formula for the scattered light for any location in an ice raster. And I give the formula here, which is just a combination of local scattered light from within 50 arcseconds of the region of interest, and also long-range scattered light from the entire solar disk. We're particularly interested in temperatures around log T 6.2, as this is where the silicon and sulfur lines are formed that I use for measuring the FIP bias, which I'll mention on the next slide. Unfortunately, what I found is that often scattered light dominates in coronal hole regions. I'm just finishing up the paper this month and should have it submitted soon, where you'll see more details about this. Okay, the FIP bias, as I mentioned, is important because we believe it is preserved from the corona into the solar wind, and so can be a signature of where the solar wind is coming from. This is particularly important for Parker Solar Probe and Solar Orbiter. The sulfur to silicon ratio is the one we get from ice, formed at log T 6.2, as I mentioned on the last slide. I've taken some code I developed for a paper 3 years ago and standardized it such that it works with the Chianti lookup tables I mentioned earlier. It takes a list of emission line measurements and automatically generates the differential emission measure curve, the DEM, and the FIP bias. I show here an example of a derived DEM and FIP bias using the MC DEM code. Other code options are available as well. And I'm busy writing another Chianti technical report. We'll explain how this procedure works so that anybody will be able to follow it. In terms of results, this slide shows an example of a coronal hole boundary observed by ice continuously for almost 24 hours. In this case, I'm able to obtain silicon to sulfur maps of the boundary region in an automated way using the software I've just described in this talk. And this slide kind of just shows the ratios derived from the method. Okay, so that's the end of my talk. To finish it, I'll just highlight that EUV slit spectrometers have a very bright future. SPICE was launched on Solar Orbiter last year, and the early data have been coming in. At the AGU last year, new beacons, as they were called, were reported by Andre Fludra, as shown in the top right image, this slide. Recently, JAXA and NASA selected the EUVST mission concept, which will be launched in 2026. This will be essentially the perfect slit spectrometer, giving seamless temperature coverage of the entire solar atmosphere at sub-arc-second spatial resolution. And I'm also hopeful that MUSE may be selected this year by NASA. This is a novel multi-slit design spectrometer that will be great for studying dynamic events such as this jet I'm showing here. So rather than scanning across the jet, you'll get simultaneous multiple slit spectra from the jet as it evolves. So by combining with the exciting new instruments on Aditya, then I think we should have a very exciting decade coming up. So thanks for your attention, and I look forward to your questions. Thank you.
Yeah, thanks for the talk, Peter. So he has joined us live. So if you have any questions, you may raise your hand and ask question directly. Yeah,
Okay.
so Krishna.
Hi, I'd just like to say hello. This is Peter Young.
Yeah, hello. Yeah, so Krishna, yeah, I saw your hand. Yeah, you can go ahead.
Hi, Peter. Thanks for this nice overview. So I have two questions, one sort of technical and one science question. So the science question is about the forbidden lines. You have shown that it is brighter than the allowed lines. Is this always the case? And is it because atoms spend more number of time there? Hello?
Oh, hi, yeah. So, yeah, in terms of the forbidden lines, yeah, it's an interesting property. It's generally the case for the ion forbidden lines that they're of comparable strength to the allowed lines. It's really a combination of what we call resonances. So the kind of the background collision strength for these transitions is low, but you get resonances at low energies, which will lead to a strong enhancement of the collision rate. And you also get the effect of that the transitions don't get directly excited. Well, they get directly excited, but also excitation goes to higher levels and then decays back down to those levels. A process called cascading, which enhances the strength of the lines as well.
Okay, my second question is a technical question about your ICE AutoFit software, which I have used previously and I regularly use. Thank you very much for making it available. So I was actually trying to use it. I was actually trying to use it try to make it parallel to try fitting multiple pixels using multiple processes, but because those inputs and outputs are structures, I was unsuccessful in doing it. Do you have any solution for that? Is my voice clear?
Say that again. So you had problems. Yeah, it's breaking a little bit, but yeah, I understood. You're running it on.
Yeah, I'm trying to run it on parallelly using multiprocessors.
Okay. Okay. Yes. I haven't tried using that. You say the problem is with the structure output. Was that correct?
Yeah. Structure output and structure input. So I cannot transfer those structure inputs to different processors. So it's a technical one. I can write for the chat and we can discuss if you want.
Okay, yes, please. Yeah, if you could send me a description of what you're doing, and I can take a look at it. Yes, certainly.
Thank you.
Thank you.
Yeah, thanks. So next, Hui, you want to go?
Yes, thank you for the nice talk, Peter. You mentioned that the kernel hole emission is dominated. Can you hear me? Okay,
yes,
so you mentioned that the kernel hole emission is dominated by the scatter light. How does this effect affect the science results about kernel holes people obtained with spectrometers such as Sumer and ICE in the past?
Yes, I think it's a problem. The amount of scattered light does vary with the observation. So particularly if the sun is completely quiet, then that reduces the full disk scattered light. And so, but still at the level of iron 12, there'll be a contribution of, maybe 30, perhaps even 50% in that case. And I think it is an issue. I know I've seen examples. If you look at the coronal hole, if you look close to the boundary, for example, you may see blue shifts close to the boundary. But as you go to the deeper part of the coronal hole, I've seen cases where the blue shift disappears. And I think that may be due to the scattered light essentially taking over, and it kind of overwhelms the Doppler shift in the coronal hole. So Yes, I think it's a potential problem, and I don't think I'm not sure about SUMA. I think it's a problem for ICE, and I think it'll be a problem for SPICE as well and Solar Orbiter. But and it's specifically for on-disk coronal holes that I was looking at. I think ideally in the future we should have a spectrometer that has some sort of a culture for looking at on-disk coronal holes. Okay.
Okay, thank you.
Yeah, thanks, Hui. Tanmay, you have a question?
Hi, Peter. This is a really nice talk. So during the starting of my I used the ICE instrument data, and it was really helpful to this software notes. You know, it was so comprehensive, and it's helped a lot. And thinking in future also for Aditya mission, this will provide a very important guideline for how to take all this correction and how to produce this software pipeline and stuff. So thank you for that. And I have a question. So since Aditya VLC don't have any sensitive density sensitive line, so my question is, are there any way to measure density from emission measure and by doing some back calculation or any other way?
Okay, yes. Yeah, it is possible to, if you don't have density diagnostics, then if you have absolute intensity measurements and you can, and an estimate of the volume that you're looking at, then you can make an estimate of the density that way. But the downside is the filling factor of the plasma is something that's unknown. So that's the great thing with the density diagnostics, that allow you to get around the filling factor issue. But certainly you can make, and people have done this for years at different wavelength regions. They can make an estimate of the electron density that way, simply by on the absolute intensity and an estimate of the volume.
Oh, okay, thank you.
Yeah, thanks. Dipankar, you may go ahead.
Yeah, hi Peter. I think for the younger colleagues over the years, Peter has helped the entire community spectroscopists. We're back in serious, and my suggestion is, if you have sometimes very exciting results, you better verify it from Peter that it is not instrumental and and not scientific. If you recall, Gidgesh has a very exciting results about 9-bit Hoffman, and I told Gidgesh, you first verify with Peter that whether we are seeing something which is could be of instrumental in nature. And thankfully, Peter did the analysis and told us that it could be instrumental, so we better not publish it. So it's a comment, and thanks again, Peter. Over the years, you have helped the entire community for these, analysis tools and so on. Yeah. Thank you.
Okay, thank you. Thank you.
Yeah, Durgesh, you can go ahead.
Hi, Peter. Good morning. Thank you for your talk.
Hi, Durgesh.
I mean, I was just simply repeat what everybody is acknowledging you for, which is very very nice, and thank you for that. I have a question about your last project. You mentioned about looking at the abundances, measuring from the coronal hole and comparing that with Parker Solar Probe. So has that connection been made, and what sort of results are you guys getting? I mean, do you find that sources are deep inside the coronal hole, or on the boundary of coronal hole and quiet sun, or what sort of results are getting out?
No, we don't have a definite result yet. I mean, it's quite a difficult problem making this connection, simply as much because the magnetic field extrapolations that you do to look for the connection to the satellite, they have inherent uncertainties themselves. And then also these issues of the abundances, I mean, ICE can measure the FET bias in different regions, but the difference between the different regions is fairly small. It's like a factor between 1 and 3. And then there's this additional issue with the scattered light, which we're finding. That was that was kind of the issue. We were looking at sort of quiet sun coronal hole boundaries. There wasn't really much of a difference between the fit bias. So then I started looking at the scatter line to see if that was a problem. So so I kind of got distracted into that technical issue. So we're still chasing the results at the moment. Yes.
Okay. Thank you.
Yeah, thank you. If there are no further questions, then yeah, I thank all the speakers again for wonderful talks and all the colleagues for nice discussion. Yeah, so over to you, Supriya.
Yeah, thank you again, all the speakers of the session. And I think we are at the end of the session, and LOC has some vote of thanks to make. I'll hand it over to the LOC.
Okay, so yeah, so I want to express my thanks to some people who made this organization of this IAA 50 conference possible. And we, as you all agree, you may agree, we had an excellent set of talks, and we made sure that the best possible summary of all the latest in solar physics is heard in this conference. And let me first start with thanking our director, Professor Annapurni Subramaniam. She supported our proposal from the solar physics group in IAA to have this conference. I thank her. And let me start here. Okay. Do you see my screen?
No.
Oh, okay. Sorry. Let me share again.
So Rajguru, you normally do the thanking in the concluding session. So after everything is over, so I'm somewhat surprised that you are doing it now. But anyway, I hope our conference summaries are on.
Yeah. So we do have an important session. I mean, I just wanted to, before our some of our LOC people go away, so they may not be there in the late evening. So I thought I would. So we will. Yeah. So do you see my screen now?
Yes.
Okay. So let me. Yeah. So I don't know. So we will. We do have a session, right? We didn't forget that. So I thought I would kind of thank certain people before, we may not be having all the people at the evening, late night. So I thought I would do this. So let me thank the scientific organizing committee members and who made sure that we get the best possible speakers, and we also discussed a lot of aspects of this meeting, including having a good balance of young and experts, young people also, and also have a good large attention to having gender balance in our presenters and speakers. And so I thank all the members of the SOC, and I also thank these people, the local organizing committee members who are here, especially the technical team, who are also, some of them are sitting here in this room. And I would especially like to thank Prasanna, who helped in the technical aspects of the Zoom, running the Zoom, everything goes smoothly. And also I thank the web team and all the website which you use to register for the conference and go through all the other details of the conference, including the poster submission and poster viewing, was made possible by Rikesh Mohan at the bottom right, you see, and also Padma Shri. So this, I would like to close this the last session of this, the regular science session. So don't forget to come back at 9 p.m. Indian time. So that will be one of the most important aspects of this conference. So that's the summary of this conference will be done by Arnav, the later half of the meeting, and the first half of the meeting by Venkatakrishnan, Professor Venkatakrishnan. So for that, we'll come back at 9 p.m. Indian time. Okay, so thank you all for coming and participating in this, virtually participating in the meeting. And I thank also all the speakers and solicitor, as well as the contributed speakers and the invited speakers, and also the poster presenters. So the posters are they will be still available in Slack channel. We won't close the Slack channel immediately. It will be available for a few more days. So I still encourage people now, at the end of the session, you still go to the Slack channel and interact with the poster presenters. Okay, so with that, let me close this session and we will come back at 9 p.m. for the summary of the conference. Okay, thank you.